You there! Stop!
Welcome to Gorm the Olds, the big ideas in mathematics, read by me, the god from Oblivion. Algebra. Algebra is a fundamental branch of mathematics that deals with symbols and the rules for manipulating these symbols to solve equations and understand relationships between quantities. It involves the study of variables, constants, expressions, equations, functions, and algebraic structures. Algebra provides a systematic way to represent and analyze mathematical problems, allowing for generalization and abstraction beyond arithmetic. Key concepts include solving linear and quadratic equations, working with polynomials, understanding inequalities, and exploring functions and their properties. Algebra serves as a foundation for advanced mathematical topics and is essential in various fields such as science, engineering, economics, and computer science. Linear algebra. Linear algebra is a branch of mathematics that studies vectors, vector spaces, also called linear spaces, linear transformations, and systems of linear equations. It provides the framework for understanding and solving problems involving linear relationships. Key concepts include vectors, matrices, determinants, eigenvalues, and eigenvectors, and linear mappings. Linear algebra is fundamental in various fields, such as engineering, physics, computer science, economics, and statistics, as it enables the modeling and analysis of multidimensional data and systems. The discipline covers operations like vector addition and scalar multiplication, matrix multiplication, and techniques for solving linear systems such as Gaussian elimination. It also explores properties of vector spaces, including subspaces, bases, dimension, and orthogonality, which are essential for understanding the structure and behavior of linear systems. Abstract algebra. Abstract algebra is a branch of mathematics that studies algebraic structures such as groups, rings, fields, modules, and algebras. Unlike elementary algebra, which deals with solving equations and manipulating expressions, abstract algebra focuses on understanding the underlying structures and their properties in a generalized and axiomatic manner. Key concepts include groups, which capture the idea of symmetry and operations with inverses, rings, which generalize arithmetic operations with addition and multiplication, and fields, which extend rings by allowing division except by zero. Abstract algebra provides the foundational language and tools for many areas of mathematics and its applications, including number theory, geometry, cryptography, and coding theory. It emphasizes the study of homomorphisms, isomorphisms, and other structure-preserving maps, enabling mathematicians to classify and analyze algebraic systems systematically. Boolean algebra. Boolean algebra is a branch of algebra that deals with variables that have two distinct values, true and false, often represented as 1 and 0 respectively. It is fundamental in the study of logic, computer science, and digital circuit design. Boolean algebra involves operations such as AND, OR, and NOT, which correspond to logical conjunction, disjunction, and negation. These operations follow specific laws and properties, including commutativity, associativity, distributivity, identity elements, and De Morgan's laws. The discipline enables the simplification of logical expressions and the design of efficient digital systems by manipulating binary variables and logical functions. Boolean algebra forms the theoretical foundation for designing and analyzing digital circuits, programming languages, and algorithms that operate on binary data. Commutative algebra. Commutative algebra is a branch of algebra that studies commutative rings, their ideals, and modules over such rings. It provides the algebraic foundation for algebraic geometry and number theory by focusing on structures where multiplication is commutative. Key concepts include rings, ideals, prime and maximal ideals, ring homomorphisms, localization, integral extensions, Noetherian rings, and modules. The subject explores properties of rings that generalize integers and polynomial rings, enabling the study of solutions to polynomial equations and algebraic varieties. Techniques from commutative algebra are essential in understanding the structure of algebraic objects and their geometric interpretations. Homological algebra. Homological algebra is a branch of mathematics that studies homology and cohomology theories in a general algebraic setting. It provides tools and concepts to analyze and classify algebraic structures using sequences of abelian groups or modules and their morphisms. Central to homological algebra are chain complexes, exact sequences, and derived functors such as ext and tor, which measure the extent to which certain algebraic constructions fail to be exact. This discipline plays a crucial role in various areas of mathematics, including algebraic topology, algebraic geometry, and representation theory. By offering a unified framework to study and compute invariants that capture deep structural properties of mathematical objects. Universal algebra. Universal algebra is a field of mathematics that studies algebraic structures in a general and abstract way. Instead of focusing on specific structures like groups, rings, or fields, universal algebra investigates common properties and principles that apply to all algebraic systems defined by operations and identities. It provides a unified framework to analyze and compare different algebraic systems by examining their operations, identities, equational laws, and homomorphisms. Key concepts include algebras, sets equipped with operations, varieties, classes of algebras defined by sets of identities, free algebras, congruences, equivalence relations compatible with operations, and homomorphisms. Universal algebra has applications in logic, computer science, and other areas of mathematics, offering tools to understand the structural aspects of algebraic theories and their interrelations. Algebraic geometry. Algebraic geometry is a branch of mathematics that studies the solutions of systems of polynomial equations using geometric methods. It combines techniques from abstract algebra, especially commutative algebra, with the language and problems of geometry. The central objects of study are algebraic varieties, which are geometric manifestations of solutions to polynomial equations. These varieties can be affine or projective, and their properties are analyzed using tools such as sheaf theory, cohomology, and schemes. Algebraic geometry provides a deep understanding of the structure and classification of these varieties, linking geometric intuition with algebraic formalism. It has applications across mathematics and theoretical physics, including number theory, complex geometry, and string theory. Algebraic number theory. Algebraic number theory is a branch of mathematics that studies the algebraic structures related to algebraic integers. It extends the familiar properties of integers to more general number systems, such as rings of integers in number fields. Central topics include the study of number fields, which are finite extensions of the rational numbers, and their ring of integers, which generalize the concept of ordinary integers. Key concepts involve prime factorization in these rings, ideal theory, class groups, and units. The field explores how unique factorization may fail in these generalized settings and introduces ideals to restore a form of unique factorization. Algebraic number theory has deep connections with other areas, such as algebraic geometry, arithmetic geometry, and cryptography, and it provides foundational tools for solving Diophantine equations and understanding the distribution of prime numbers. Computational algebra. Computational algebra is a branch of mathematics that focuses on the development and implementation of algorithms to solve problems in algebra. It involves the use of computer algebra systems to perform symbolic computations, such as polynomial factorization, solving systems of algebraic equations, and manipulating algebraic structures like groups, rings, and fields. This field bridges abstract algebraic theory with practical computational techniques, enabling efficient handling of complex algebraic problems that are otherwise difficult to solve manually. Key areas include algorithm design, complexity analysis, and applications in cryptography, coding theory, and automated theorem proving. Non-associative algebra. Non-associative algebra is a branch of algebra that studies algebraic structures in which the associative law does not necessarily hold. Unlike associative algebras, where the equation AB, CE equals a BC, is always true for any elements A, B, and C, non-associative algebras relax this requirement, allowing for more general and diverse structures. This field encompasses various important algebraic systems, such as Lie algebras, Jordan algebras, alternative algebras, and quasi-groups. These structures arise naturally in different areas of mathematics and physics, including geometry, quantum mechanics, and the theory of differential equations. The study of non-associative algebras involves understanding their identities, representations, derivations, and cohomology, as well as their applications in modeling symmetries and other phenomena where associativity is not present or not desired. Geometry. Geometry is a branch of mathematics concerned with the properties and relations of points, lines, surfaces, and solids in space. It studies the size, shape, relative position of figures, and the properties of space. The field is traditionally divided into plane geometry, which deals with two-dimensional figures like triangles, circles, and polygons, and solid geometry, which focuses on three-dimensional objects, such as spheres, cubes, and cylinders. Key concepts include points, lines, angles, surfaces, and volumes, as well as theorems and postulates that describe their relationships. Geometry has applications in various fields including physics, engineering, architecture, and computer graphics, providing tools to model and analyze spatial structures and phenomena. Euclidean geometry. Euclidean geometry is a branch of mathematics that studies the properties and relations of points, lines, angles, surfaces, and solids in a flat, two-dimensional plane or three-dimensional space, based on the postulates and axioms formulated by the ancient Greek mathematician Euclid. It is characterized by the use of a set of 5 fundamental postulates, including the famous parallel postulate, which states that through a point not on a given line, there is exactly one line parallel to the given line. Euclidean geometry covers concepts such as congruence, similarity, the Pythagorean theorem, the properties of triangles, circles, polygons, and the measurement of angles and distances. It forms the foundation of classical geometry and is widely applied in various fields, including architecture, engineering, physics, and computer graphics. Unlike non-Euclidean geometries, Euclidean geometry assumes a flat space where the usual rules of distance and angle measurement apply. Non-Euclidean geometry. Non-Euclidean geometry is a branch of mathematics that explores geometrical systems that do not adhere to the postulates of Euclidean geometry, particularly the parallel postulate. Unlike Euclidean geometry, where through a point not on a given line there is exactly one parallel line, non-Euclidean geometries modify this axiom, leading to fundamentally different properties and structures. The two main types of non-Euclidean geometry are hyperbolic geometry and elliptic geometry. Hyperbolic geometry assumes that through a point not on a given line, there are infinitely many lines that do not intersect the original line, resulting in a space with constant negative curvature. Elliptic geometry, on the other hand, assumes no parallel lines exist, corresponding to a space with constant positive curvature, like the surface of a sphere. These geometries have profound implications in various fields, including physics, particularly in the theory of general relativity, where the fabric of spacetime is modeled using non-Euclidean geometry. The study of non-Euclidean geometry challenges the traditional notions of space and has expanded the understanding of mathematical structures and their applications. Analytic geometry. Analytic geometry, also known as coordinate geometry or Cartesian geometry, is a branch of mathematics that uses algebraic equations to represent and analyze geometric shapes and figures. It bridges algebra and geometry by describing geometric objects, such as points, lines, curves, and surfaces, using coordinate systems, typically the Cartesian coordinate system. In this framework, each point in a plane is identified by an ordered pair of numbers, x, y, and in three-dimensional space by a triplet, x, y, z. Analytic geometry allows the study of geometric properties and relationships through algebraic equations and inequalities. Key concepts include the distance formula, midpoint formula, slope of a line, equations of lines and circles, conic sections, ellipses, parabolas, and hyperbolas, and the use of vectors and parametric equations. This approach provides powerful tools for solving geometric problems, proving theorems, and modeling real-world phenomena in physics, engineering, and computer graphics. Differential geometry. Differential geometry is a branch of mathematics that uses the techniques of calculus and linear algebra to study problems in geometry. It focuses on the properties and structures of curves, surfaces, and higher-dimensional manifolds that are smooth and differentiable. Key concepts include differentiable manifolds, tangent spaces, vector fields, differential forms, and Riemannian metrics. Differential geometry provides the mathematical framework for understanding curvature, geodesics, and topological properties of spaces, and it has important applications in physics, particularly in the theory of general relativity, as well as in engineering and computer science. Algebraic geometry. Algebraic geometry is a branch of mathematics that studies the solutions of systems of polynomial equations using geometric methods. It combines techniques from abstract algebra, especially commutative algebra, with the language and problems of geometry. The central objects of study are algebraic varieties, which are geometric manifestations of these polynomial solutions. Algebraic geometry explores properties such as dimension, singularities, and morphisms between varieties, providing a deep understanding of their structure and classification. This field has profound connections with number theory, complex analysis, and topology, and it plays a crucial role in modern mathematical research and applications, including cryptography, coding theory, and theoretical physics. Discrete geometry. Discrete geometry is a branch of mathematics that studies geometric objects and properties that are fundamentally discrete or combinatorial rather than continuous. It focuses on configurations of distinct and separated points, lines, polygons, polyhedra, and other discrete sets in Euclidean space and other geometric settings. Key topics include the study of convex polytopies, tilings, packings, arrangements of lines and hyperplanes, and geometric graphs. Discrete geometry has strong connections with combinatorics, computational geometry, and optimization, and it plays a crucial role in computer science, particularly in algorithms and data structures related to spatial data. Unlike classical geometry, which often deals with smooth curves and surfaces, discrete geometry emphasizes finite or countable collections of geometric elements and their combinatorial properties. Computational geometry. Computational geometry is a branch of mathematics and computer science that focuses on the study of algorithms and data structures for solving geometric problems. It involves the design, analysis, and implementation of efficient algorithms to handle geometric objects such as points, lines, polygons, and polyhedra. Key topics include convex hulls, Voronoi diagrams, Delaunay triangulations, range searching, and motion planning. Computational geometry has applications in computer graphics, robotics, geographic information systems, GIS, computer-aided design, CAD, and more. The field bridges theoretical mathematics with practical computational techniques to address spatial problems and optimize geometric computations. Projective geometry. Projective geometry is a branch of mathematics that studies the properties of geometric figures that are invariant under projective transformations. Unlike Euclidean geometry, which focuses on measurements such as distances and angles, projective geometry emphasizes the relationships between points, lines, and planes, particularly those that remain unchanged when the figures are projected from one plane to another. Key concepts include points at infinity, the principle of duality, where points and lines can be interchanged, and the cross ratio, an invariant under projective transformations. Projective geometry provides a unified framework for understanding perspective in art, computer graphics, and various areas of mathematics, including algebraic geometry and topology. It originated from the study of perspective in Renaissance art and has since evolved into a fundamental area of modern geometry. Convex geometry. Convex geometry is a subfield of geometry that studies convex sets, primarily in Euclidean space. A set is convex if, for any 2 points within the set, the line segment connecting them lies entirely inside the set. This property leads to many important geometric and analytic results. Convex geometry explores properties of convex bodies, convex functions, and their interactions with linear algebra and optimization. Key concepts include convex hulls, supporting hyperplanes, Minkowski addition, and separation theorems. Applications of convex geometry span optimization theory, functional analysis, and computational geometry, making it a fundamental area in both pure and applied mathematics. Topology. Topology is a branch of mathematics concerned with the properties of space that are preserved under continuous deformations, such as stretching, twisting, crumpling, and bending, but not tearing or gluing. It studies concepts such as continuity, compactness, connectedness, and convergence, providing a framework to analyze spatial properties that remain invariant under homeomorphisms. Topology can be divided into several subfields, including point-set topology, which focuses on the foundational aspects and structures of topological spaces, algebraic topology, which uses tools from abstract algebra to study topological spaces, and differential topology, which deals with differentiable functions on differentiable manifolds. The discipline has applications in many areas of mathematics and science, including geometry, analysis, and mathematical physics, and serves as a fundamental language for understanding the qualitative aspects of geometric structures. Calculus. Calculus is a branch of mathematics focused on the study of change and motion. It is divided into 2 main areas: differential calculus and integral calculus. Differential calculus concerns the concept of the derivative, which represents the rate of change of a function with respect to a variable. It is used to find slopes of curves, optimize functions, and model dynamic systems. Integral calculus deals with the concept of the integral, which represents the accumulation of quantities and the area under curves. It is used to calculate areas, volumes, and solve problems involving accumulation. The fundamental theorem of calculus links these 2 areas by showing that differentiation and integration are inverse processes. Calculus has broad applications across science, engineering, economics, and beyond, providing tools to analyze and model continuous change. Differential calculus. Differential calculus is a branch of mathematics that focuses on the concept of the derivative, which represents the rate at which a function changes at any given point. It is a fundamental tool for analyzing and understanding the behavior of functions, particularly in terms of their slopes, rates of change, and local linear approximations. The core idea is to study how a function's output value changes as its input changes infinitesimally. Key concepts include limits, continuity, the definition of the derivative, differentiation rules, such as the product, quotient, and chain rules, and applications like finding tangent lines, optimizing functions, and solving problems involving motion and change. Differential calculus serves as the foundation for many advanced topics in mathematics, physics, engineering, and economics, providing essential techniques for modeling and solving real-world problems involving dynamic systems. Integral calculus. Integral calculus is a fundamental branch of mathematics that focuses on the concept of integration, which is essentially the reverse process of differentiation. It deals with finding the integral of functions, which can be interpreted as the accumulation of quantities, such as areas under curves, volumes, and other related measures. Integral calculus is divided into two main types: definite integrals and indefinite integrals. An indefinite integral represents a family of functions and includes an arbitrary constant, while a definite integral calculates the exact accumulation between two limits and results in a numerical value. The fundamental theorem of calculus links differentiation and integration, showing that they are inverse processes. Integral calculus has wide applications in physics, engineering, economics, and beyond, enabling the calculation of quantities like displacement, area, volume, and total accumulated change. Multivariable calculus. Multivariable calculus is a branch of mathematics that extends the concepts of single-variable calculus to functions of multiple variables. It involves the study of limits, continuity, differentiation, and integration for functions with two or more variables. Key topics include partial derivatives, which measure how a function changes as one variable changes while others are held constant; gradient vectors, which indicate the direction and rate of fastest increase of a function; multiple integrals, such as double and triple integrals, used to compute volumes and other quantities over regions in higher dimensional spaces; and vector calculus concepts like divergence, curl, and line and surface integrals. Applications of multivariable calculus are widespread in physics, engineering, economics, and other fields where systems depend on multiple variables simultaneously. This discipline provides the mathematical tools to analyze and optimize multivariate systems and to model phenomena in three-dimensional space and beyond. Vector calculus. Vector calculus is a branch of mathematics that deals with differentiation and integration of vector fields, primarily in 2 or 3 dimensions. It extends the concepts of calculus to vector-valued functions, allowing the analysis of quantities that have both magnitude and direction. Key operations in vector calculus include the gradient, divergence, curl, and Laplacian, which provide measures of rate of change, flux, and rotation of vector fields. Fundamental theorems such as Green's theorem, Stokes' theorem, and the divergence theorem connect the behavior of vector fields within a region to their behavior on the boundary, enabling the evaluation of complex integrals. Applications of vector calculus are widespread in physics and engineering, particularly in electromagnetism, fluid dynamics, and the study of forces and motion. Differential equations. Differential equations are mathematical equations that relate a function with its derivatives. They play a crucial role in modeling various phenomena in physics, engineering, biology, and economics, where the rate of change of a quantity is of interest. The study of differential equations involves finding functions that satisfy these equations, which can be ordinary differential equations, ODEs, involving derivatives with respect to a single variable, or partial differential equations, PDEs, involving multiple variables. Techniques for solving differential equations include separation of variables, integrating factors, characteristic equations, and numerical methods. Understanding differential equations is fundamental in calculus as it extends the concept of derivatives and integrals to dynamic systems and processes. Calculus of variations. Calculus of variations is a field of mathematical analysis that deals with optimizing functionals, which are mappings from a set of functions to the real numbers, unlike traditional calculus that focuses on functions and their derivatives. The calculus of variations seeks to find a function that minimizes or maximizes a given functional. This discipline has its roots in problems such as finding the shortest path between 2 points, the shape of a hanging cable, catenary, or the curve that a light ray follows to minimize travel time. Fermat's principle. The fundamental problem typically involves determining a function y of x that makes an integral of the form j of y equals integral from a to bf of xy prime of x dx stationary, meaning that the first variation of j is 0. The Euler-Lagrange equation provides a necessary condition for this extremum and is derived by considering small variations of the function y of x. Solutions to these equations yield functions that optimize the functional. Calculus of variations has profound applications in physics, engineering, economics, and other sciences, particularly in mechanics, optics, and control theory, where systems are often described by principles of least action or optimality. Real analysis. Real analysis is a branch of mathematical analysis dealing with real numbers and real valued functions. It rigorously studies concepts such as sequences and series, limits, continuity, differentiation, integration, and convergence. The field provides the theoretical foundation for calculus by formalizing the intuitive notions of limits and infinitesimals. Key topics include the properties of real numbers, completeness, metric spaces, and various modes of convergence. Real analysis is essential for understanding the behavior of functions and for proving results in calculus, differential equations, and other areas of mathematics. Complex analysis. Complex analysis is a branch of mathematics that studies functions of complex variables. It extends the concepts of calculus to the complex plane, where numbers have both real and imaginary parts. Key topics include analytic functions, which are complex functions differentiable at every point in their domain, and conformal mappings, which preserve angles and shapes locally. The theory involves powerful results such as Cauchy's integral theorem and formula, which provide integral representations for analytic functions and lead to important consequences like the existence of Taylor and Laurent series expansions. Complex analysis also explores singularities, residues, and contour integration, which have applications in evaluating real integrals and solving physical problems. This discipline is fundamental in many areas of mathematics and physics due to its elegant structure and wide applicability. Statistics. Statistics is a branch of mathematics that deals with the collection, analysis, interpretation, presentation, and organization of data. It provides tools and methodologies to summarize complex data sets, identify patterns, and make informed decisions based on data. The field is broadly divided into descriptive statistics, which focuses on summarizing and describing data features through measures like mean, median, mode, variance, and standard deviation, and inferential statistics, which involves making predictions or inferences about a population based on a sample using techniques such as hypothesis testing, confidence intervals, and regression analysis. Statistics is foundational in various disciplines including science, economics, engineering, and social sciences, enabling researchers to validate models, test theories, and support decision-making under uncertainty. Descriptive statistics. Descriptive statistics is a branch of statistics that involves summarizing and organizing data so it can be easily understood. It includes methods for describing the central tendency, variability, and distribution shape of a dataset. Common measures of central tendency are the mean, median, and mode, which indicate the average or most typical values. Measures of variability include range, variance, and standard deviation, which describe the spread or dispersion of data points. Descriptive statistics also involve graphical representations, such as histograms, box plots, and bar charts to visualize data patterns. These techniques provide foundational insights into data before applying inferential statistics and are essential for data analysis in various fields. Inferential statistics. Inferential statistics is a branch of statistics that focuses on making predictions, decisions, or inferences about a population based on a sample of data drawn from that population. Unlike descriptive statistics, which merely summarizes data, inferential statistics uses probability theory to estimate population parameters, test hypotheses, and make forecasts. Key concepts include estimation, point estimates and confidence intervals, hypothesis testing, null and alternative hypotheses, type 1 and 2 errors, p-values, and regression analysis. Techniques such as t-tests, chi-square tests, ANOVA, and correlation analysis are commonly employed. Inferential statistics is essential in fields where it is impractical or impossible to collect data from an entire population, enabling researchers to draw conclusions and make informed decisions with quantifiable uncertainty. Probability theory. Probability theory is a branch of mathematics concerned with the analysis of random phenomena. It provides a formal framework for quantifying uncertainty and modeling the likelihood of various outcomes. Central to probability theory are concepts such as random variables, probability distributions, expectation, variance, and events. The theory is built upon axioms introduced by Andrei Kolmogorov, which define probability as a measure satisfying certain properties over a sigma algebra of events. Probability theory underpins statistical inference, stochastic processes, and numerous applications across science, engineering, economics, and beyond. It enables the rigorous study of phenomena where outcomes are uncertain, facilitating predictions, decision-making, and risk assessment. Bayesian statistics. Bayesian statistics is a branch of statistics based on Bayes' theorem, which provides a mathematical framework for updating probabilities as new evidence or data becomes available. Unlike frequentist statistics, which interprets probability as the long-run frequency of events, Bayesian statistics treats probability as a measure of belief or certainty about an event. The core idea is to combine prior knowledge, prior probability, with observed data, likelihood, to produce an updated probability, posterior probability. This approach allows for a coherent and flexible method of statistical inference, enabling the incorporation of expert knowledge and the handling of complex models. Bayesian methods are widely used in various fields, such as machine learning, decision theory, and scientific research, offering advantages in parameter estimation, hypothesis testing, and predictive modeling. Non-parametric statistics. Non-parametric statistics is a branch of statistics that does not assume a specific probability distribution for the data. Unlike parametric methods, which rely on parameters defined by a fixed distribution, such as the mean and variance in a normal distribution, non-parametric methods are distribution-free and can be applied to data that do not meet these assumptions. This makes non-parametric statistics particularly useful for analyzing ordinal data, ranked data, or data with unknown or complex distributions. Common techniques in non-parametric statistics include rank-based tests like the Wilcoxon signed rank test, the Mann-Whitney-U test, and the Kruskal-Wallis test, as well as methods like kernel density estimation and the bootstrap. These methods are widely used in hypothesis testing, estimation, and regression analysis when the underlying data distribution is unknown or when sample sizes are small. Overall, non-parametric statistics provide flexible and robust tools for analyzing data without relying on strict distributional assumptions, making them essential in many practical applications across various fields of mathematics and statistics. Multivariate statistics. Multivariate statistics is a branch of statistics that involves the observation and analysis of more than one statistical outcome variable at a time. It encompasses a variety of techniques used to analyze data that arises from more than one variable, allowing researchers to understand relationships, patterns, and structures within complex data sets. Key methods include multivariate regression, principal component analysis, PCA, factor analysis, cluster analysis, and discriminant analysis. These techniques help in reducing dimensionality, identifying latent variables, classifying observations, and modeling the interdependencies among variables. Multivariate statistics is widely applied in fields such as economics, biology, psychology, and engineering, where multiple measurements are collected simultaneously and their joint behavior is of interest. Time series analysis. Time series analysis is a branch of statistics and mathematics that deals with the analysis of data points collected or recorded at successive points in time. The primary goal is to understand the underlying structure and function that produce the observed data, to model the temporal dependencies, and to forecast future values based on historical patterns. Key concepts include stationarity, autocorrelation, seasonality, and trend components. Common models used in time series analysis are autoregressive, AR, moving average, MA, autoregressive integrated moving average, ARIMA, and seasonal ARIMA, SARIMA. Techniques such as spectral analysis, decomposition, and state space models are also employed. Applications of time series analysis span economics, finance, meteorology, engineering, and many other fields where data is naturally ordered in time. Statistical quality control. Statistical quality control, SQC, is a branch of statistics focused on using statistical methods to monitor and control a process to ensure that it operates at its full potential to produce conforming products. It involves the application of statistical techniques such as control charts, process capability analysis, and design of experiments to detect and reduce variability in manufacturing and service processes. The primary goal of SQC is to maintain consistent quality by identifying and eliminating sources of variation, thereby improving product reliability and customer satisfaction. Key components include descriptive statistics, sampling inspection, and hypothesis testing, which together help in making informed decisions about process adjustments and quality improvements. Biostatistics. Biostatistics is a specialized branch of statistics that applies statistical methods to the field of biology, particularly in medicine, public health, and biology-related research. It involves the design of biological experiments, the collection and analysis of data from those experiments, and the interpretation of results to draw meaningful conclusions. Key areas within biostatistics include hypothesis testing, regression analysis, survival analysis, and the analysis of clinical trials. Biostatisticians play a crucial role in developing new medical treatments, understanding disease patterns, and improving healthcare outcomes by providing rigorous quantitative evidence. This discipline bridges mathematics and biology, leveraging statistical theory and techniques to address complex biological questions and support evidence-based decision-making in health sciences. Spatial statistics. Spatial statistics is a subfield of statistics that focuses on the analysis and interpretation of data that have a spatial component. It involves techniques and models that account for the spatial arrangement of data points, recognizing that observations located near each other in space may be more similar than those further apart. This discipline is essential for understanding spatial patterns, spatial dependence, and spatial heterogeneity in various fields such as geography, environmental science, epidemiology, and urban planning. Key concepts in spatial statistics include spatial autocorrelation, variograms, kriging, point pattern analysis, and spatial regression models. These tools help in modeling spatial processes, making predictions at unsampled locations, and testing hypotheses about spatial phenomena. Overall, spatial statistics integrates mathematical theories from probability, geometry, and linear algebra with statistical inference to analyze spatially referenced data effectively. Statistical computing. Statistical computing is a subfield of statistics and computational mathematics that focuses on the development and application of computational algorithms and techniques to analyze and interpret data. It encompasses a wide range of methods including simulation, numerical optimization, and data visualization, which are essential for handling complex statistical models and large data sets. Key components of statistical computing include the implementation of statistical methods in software, the use of programming languages such as R, Python, and MATLAB, and the development of efficient algorithms for tasks like parameter estimation, hypothesis testing, and predictive modeling. This discipline plays a crucial role in modern data analysis by enabling statisticians and data scientists to perform robust, scalable, and reproducible analyses, thereby facilitating informed decision-making across various scientific and industrial domains. Experimental design. Experimental design in mathematics, particularly within statistics, refers to the systematic planning of experiments to ensure that data collected can provide valid and objective conclusions. It involves selecting appropriate methods for assigning treatments to experimental units, controlling for variability, and minimizing bias and confounding factors. Key components include randomization, replication, and blocking, which help in isolating the effects of the factors under study. Experimental design enables researchers to efficiently explore relationships between variables, test hypotheses, and make inferences about populations based on sample data. Common types of experimental designs include completely randomized designs, randomized block designs, factorial designs, and crossover designs. The mathematical foundation of experimental design involves combinatorics, probability theory, and statistical inference, ensuring that experiments yield reliable and reproducible results. Probability. Probability is a branch of mathematics that deals with the study of uncertainty and the likelihood of events occurring. It provides a framework for quantifying and analyzing random phenomena by assigning numerical values, called probabilities, to events within a defined sample space. The probability of an event ranges from 0 to 1, where 0 indicates impossibility and 1 indicates certainty. Key concepts in probability include random experiments, sample spaces, events, and probability measures. Probability theory encompasses various models, such as classical, empirical, and axiomatic approaches. It also involves important rules and theorems, like the addition and multiplication rules, conditional probability, Bayes' theorem, and the law of large numbers. Probability is foundational to statistics, risk assessment, decision theory, and many applied fields such as finance, engineering, and science, enabling the prediction and understanding of random processes and outcomes. Probability theory. Probability theory is a branch of mathematics concerned with the analysis of random phenomena. It provides a formal framework for quantifying uncertainty and modeling the likelihood of various outcomes. The fundamental concepts include random experiments, sample spaces, events, and probability measures. Probability theory uses axioms, primarily those formulated by Kolmogorov, to assign probabilities to events in a consistent manner. Key topics within probability theory include conditional probability, independence, random variables, probability distributions, expectation, variance, and limit theorems such as the law of large numbers and the central limit theorem. This theory underpins many applied fields such as statistics, finance, engineering, and science, enabling the rigorous study of stochastic processes and decision-making under uncertainty. Random variables. In mathematics, particularly in probability theory, a random variable is a variable whose possible values are numerical outcomes of a random phenomenon. Formally, a random variable is a measurable function from a sample space of a random experiment to the real numbers. There are two main types of random variables: discrete and continuous. A discrete random variable takes on a countable number of distinct values, often integers, such as the result of rolling a die. A continuous random variable can take on any value within an interval or collection of intervals, such as the exact height of a randomly selected person. Random variables are fundamental in defining probability distributions, which describe the likelihood of each possible outcome. Key concepts associated with random variables include the probability mass function, PMF, for discrete variables, the probability density function, PDF, for continuous variables, cumulative distribution functions, CDF, expectation, mean, variance, and higher moments. Understanding random variables enables the modeling and analysis of uncertainty and variability in various fields, such as statistics, engineering, finance, and science. Probability distributions. Probability distributions are mathematical functions that describe the likelihood of different outcomes in a random experiment. They provide a complete description of the probabilities associated with each possible value or range of values of a random variable. Probability distributions can be discrete or continuous. Discrete probability distributions assign probabilities to distinct, separate values, such as the number of heads in coin tosses, with examples including the binomial, Poisson, and geometric distributions. Continuous probability distributions describe probabilities over a continuous range of values, such as heights or weights, with common examples being the normal, Gaussian, exponential, and uniform distributions. Each distribution is characterized by parameters that define its shape and behavior, such as mean and variance. Understanding probability distributions is fundamental in statistics and data analysis, as they underpin hypothesis testing, estimation, and predictive modeling. Stochastic processes. Stochastic processes are mathematical objects used to model systems or phenomena that evolve over time in a way that is inherently random. Formally, a stochastic process is a collection of random variables indexed by time or space, representing the evolution of some system of random values. These processes are fundamental in probability theory and have applications across various fields, such as physics, finance, biology, and engineering. Key concepts in stochastic processes include Markov chains, Poisson processes, Brownian motion, and martingales. Markov chains describe systems that transition between states with probabilities, depending only on the current state, not the past history. Poisson processes model random events occurring independently over time, often used in queuing theory and telecommunications. Brownian motion represents continuous time random motion, foundational in modeling stock prices and physical diffusion. Martingales are processes with a conditional expectation property that makes them useful in fair game modeling and financial mathematics. Understanding stochastic processes involves studying their distributions, dependence structures, long-term behavior, and convergence properties, providing powerful tools for analyzing random phenomena evolving over time. Bayesian probability. Bayesian probability is a framework within probability theory that interprets probability as a measure of belief or certainty rather than frequency. It is based on Bayes' theorem, which provides a mathematical rule for updating the probability of a hypothesis as new evidence or data becomes available. The theorem states that the posterior probability of a hypothesis given observed data is proportional to the likelihood of the data given the hypothesis multiplied by the prior probability of the hypothesis. Formally, Bayes' theorem is expressed as P of H given D equals P of D given H times P of H divided by P of D, where H is the hypothesis and D is the data. This approach allows for the incorporation of prior knowledge or beliefs and is widely used in various fields such as statistics, machine learning, and decision-making. Bayesian probability contrasts with frequentist probability by focusing on subjective probability and updating beliefs rather than long-run frequencies of events. Markov chains. Markov chains are mathematical systems that undergo transitions from one state to another within a finite or countable state space. They are characterized by the Markov property, which states that the future state depends only on the current state and not on the sequence of events that preceded it. Formally, a Markov chain is a sequence of random variables x sub 0, x sub 1, x sub 2, and so on, with the property that p of x sub n plus 1 equals x given x sub n equals x sub n, and so on. X sub 0 equals x sub 0 equals p of x sub n plus 1 equals x given x sub n equals x sub n. The transitions are typically described by a transition matrix, where each entry represents the probability of moving from one state to another. Markov chains are used to model a variety of stochastic processes in fields such as physics, economics, biology, and computer science. Key concepts include classification of states, transient recurrent, stationary distributions, ergodicity, and mixing times. Understanding Markov chains involves studying their long-term behavior, convergence properties, and applications in areas like queuing theory, statistical mechanics, and algorithm design. Limit theorems. Limit theorems in probability theory are fundamental results that describe the behavior of sequences of random variables as the number of variables grows large. They provide the theoretical foundation for understanding convergence concepts and the long-term behavior of stochastic processes. The most important limit theorems include the law of large numbers, LLN, and the central limit theorem, CLT. The law of large numbers states that the sample average of independent and identically distributed random variables converges to the expected value as the sample size increases, ensuring stability of long-term averages. The central limit theorem states that, under certain conditions, the normalized sum of independent random variables tends toward a normal distribution regardless of the original distribution of the variables, which explains the ubiquitous appearance of the normal distribution in statistics. Other notable limit theorems include the weak law of large numbers, the strong law of large numbers, the Lindeberg-Feller central limit theorem, and various invariance principles. These theorems are essential in fields such as statistics, econometrics, and any domain involving probabilistic modeling and inference. Statistical inference. Statistical inference is a branch of statistics that focuses on drawing conclusions about a population based on data sampled from it. It involves methods for estimating population parameters, testing hypotheses, and making predictions. The process typically begins with the collection of data through random sampling, ensuring that the sample represents the population. Key concepts include point estimation, where a single value is used to estimate an unknown parameter, interval estimation, which provides a range of plausible values for the parameter, and hypothesis testing, which assesses the evidence against a specified claim about the population. Statistical inference relies on probability theory to quantify uncertainty and make probabilistic statements about the parameters. Common techniques include maximum likelihood estimation, Bayesian inference, and the use of confidence intervals and p-values. Overall, statistical inference enables informed decision-making and scientific conclusions by systematically analyzing data and accounting for variability and randomness inherent in real-world observations. Combinatorial probability. Combinatorial probability is a branch of probability theory that deals with calculating the likelihood of events by counting the number of favorable outcomes relative to the total number of possible outcomes using combinatorial methods. It involves techniques such as permutations, combinations, and the fundamental counting principle to systematically enumerate outcomes in finite sample spaces. This approach is particularly useful when dealing with discrete events where outcomes are equally likely, such as drawing cards from a deck, rolling dice, or selecting objects from a set. By leveraging combinatorial formulas, one can determine probabilities without enumerating every possible outcome explicitly, making it an essential tool in solving problems involving arrangements, selections, and distributions within a finite context. Measure-theoretic probability. Measure-theoretic probability is a rigorous mathematical framework for probability theory that uses measure theory to define and analyze probabilistic concepts. It provides a foundation for probability by modeling random phenomena as measurable functions on a measure space, typically a probability space, omega, Fp, where omega is the sample space, F is a sigma algebra of events, and P is a probability measure assigning probabilities to events. This approach generalizes classical probability and allows for handling more complex scenarios, such as continuous random variables, infinite dimensional spaces, and stochastic processes. Key concepts include measurable functions, random variables, expectation defined as an integral with respect to the probability measure, conditional expectation, independence, convergence of random variables, and laws of large numbers. Measure-theoretic probability is essential for advanced topics in probability, statistics, and stochastic analysis, providing the tools to rigorously prove results and develop theories in these areas. Number theory. Number theory is a branch of pure mathematics devoted primarily to the study of the integers and integer-valued functions. It explores properties and relationships of numbers, particularly integers, including concepts such as divisibility, prime numbers, greatest common divisors, modular arithmetic, and Diophantine equations. Key topics include the distribution of primes, congruences, factorization, and arithmetic functions. Number theory has applications in cryptography, computer science, and mathematical problem-solving, making it a fundamental and rich area of mathematical research. Divisibility theory. Divisibility theory is a fundamental area within number theory that studies the properties and relationships of integers with respect to division. It focuses on understanding when one integer divides another without leaving a remainder, denoted as a divides b or a divides b. Key concepts include divisors, multiples, prime numbers, greatest common divisors, GCD, least common multiples, LCM, and the Euclidean algorithm for efficiently computing the GCD. Divisibility theory also explores important results such as the fundamental theorem of arithmetic, which states that every integer greater than 1 can be uniquely factored into prime numbers. This theory provides the foundation for more advanced topics in algebra and number theory, including modular arithmetic, Diophantine equations, and cryptographic algorithms. Prime numbers. Prime numbers are natural numbers greater than 1 that have no positive divisors other than 1 and themselves. They are the building blocks of number theory because every integer greater than 1 can be uniquely factored into prime numbers, a property known as the fundamental theorem of arithmetic. Prime numbers play a crucial role in various areas of mathematics and its applications, including cryptography, computer science, and pure mathematical research. Key concepts related to prime numbers include primality testing, the distribution of primes, studied through the prime number theorem, and special classes of primes such as twin primes, Mersenne primes, and Fermat primes. Understanding prime numbers involves exploring their properties, patterns, and the algorithms used to identify them. Congruences. In mathematics, particularly in number theory, congruences are a way to express that two integers have the same remainder when divided by a given positive integer, called the modulus. Formally, for integers a, b, and a positive integer m, we say that a is congruent to b modulo m, written as a adig b mod m. If m divides the difference a minus b, this means there exists an integer k such that a minus b equals km. Congruences are fundamental in modular arithmetic, which studies arithmetic operations within a fixed modulus. They are widely used in solving problems related to divisibility, cryptography, computer science, and algebra. Key properties of congruences include reflexivity, symmetry, transitivity, and compatibility with addition, subtraction, and multiplication. For example, if A adeg B mod m and C adeg D mod em, then a plus C adeg B plus D mod em and a times C adeg B times D mod em. Solving congruences often involves finding all integers x, satisfying an equation like ax plus b, mod em, which can be approached using the Euclidean algorithm and modular inverses. The theory extends to systems of congruences, with the Chinese remainder theorem providing conditions for their simultaneous solutions. Overall, congruences provide a powerful framework for understanding and manipulating integers under modular constraints. Diophantine equations. Diophantine equations are polynomial equations, usually with two or more unknowns, for which only integer solutions are sought. Named after the ancient Greek mathematician Diophantus, these equations form a central area of study in number theory. The primary challenge in Diophantine equations is to determine whether solutions exist, and if so, to find all such integer solutions. Problems range from simple linear equations to complex non-linear forms, including famous cases like Fermat's last theorem and Pell's equation. Techniques for solving Diophantine equations involve a variety of mathematical tools, such as modular arithmetic, factorization methods, the theory of elliptic curves, and computational algorithms. The study of these equations has deep connections to algebra, geometry, and cryptography, making them a rich and active field of mathematical research. Arithmetic functions. Arithmetic functions are functions defined on the set of positive integers and taking values typically in the complex numbers, which arise naturally in number theory. They often encode important properties of integers, such as divisibility, prime factorization, and the distribution of primes. Common examples include the divisor function, which counts the number of divisors of an integer, the sum of divisors function, which sums all divisors of an integer, Euler's totient function, which counts the number of positive integers up to a given integer that are relatively prime to it, and the Mobius function, which is used in inversion formulas and has values depending on the prime factorization of the integer. Arithmetic functions can be multiplicative or additive, depending on how they behave with respect to the multiplication of integers. They play a crucial role in analytic number theory, especially in the study of the Riemann zeta function and Dirichlet series, and are instrumental in understanding the structure and properties of integers. Modular arithmetic. Modular arithmetic is a system of arithmetic for integers, where numbers wrap around upon reaching a certain value called the modulus. It is a fundamental concept in number theory and has applications in computer science, cryptography, and coding theory. In modular arithmetic, two integers are considered equivalent if they have the same remainder when divided by the modulus. Formally, for a positive integer n, the modulus, two integers a and b are congruent modulo n if n divides their difference, a minus b. This is written as a adeg b mod n. Operations such as addition, subtraction, and multiplication can be performed within this system, and the results are taken modulo n. Modular arithmetic simplifies computations in many areas, including solving congruences, working with cyclic structures, and analyzing periodic phenomena. Quadratic residues. Quadratic residues are a fundamental concept in number theory, specifically in the study of modular arithmetic. Given a modulus n, an integer a is called a quadratic residue modulo n if there exists an integer x, such that x not less than or equal to a mod n. In other words, a is a quadratic residue modulo n if it is congruent to a perfect square modulo n. If no such x exists, then a is called a quadratic non-residue modulo n. The study of quadratic residues is closely related to the properties of prime numbers and the structure of the multiplicative group of integers modulo n. One of the central results in this area is the law of quadratic reciprocity, which provides a criterion to determine whether a number is a quadratic residue modulo an odd prime. Quadratic residues have applications in various areas, including cryptography, primality testing, and the construction of certain types of sequences and codes. Understanding quadratic residues involves exploring concepts such as the Legendre symbol, the Jacobi symbol, and Euler's criterion, which provide tools to efficiently determine the quadratic residuosity of numbers, modulo primes, and composite moduli. Algebraic number theory. Algebraic number theory is a branch of number theory that uses techniques from abstract algebra to study the properties of algebraic integers. It focuses on the structure and behavior of number fields, which are finite extensions of the rational numbers, and their rings of integers. Key concepts include the study of prime factorization in these rings, ideal theory, class groups, and units. This field generalizes classical number theory by exploring solutions to polynomial equations with integer coefficients in more complex number systems. It has deep connections with other areas of mathematics, such as algebraic geometry, representation theory, and arithmetic geometry, and plays a crucial role in modern cryptography and coding theory. Analytic number theory. Analytic number theory is a branch of number theory that uses techniques from mathematical analysis to solve problems about integers and prime numbers. It involves the study of functions such as the Riemann zeta function and L functions, which encode properties of prime numbers and their distribution. Central topics include the distribution of prime numbers, the prime number theorem, Dirichlet characters, and the study of arithmetic functions through generating functions and complex analysis. Analytic number theory provides powerful tools to understand the asymptotic behavior of number-theoretic functions and has deep connections with other areas of mathematics, such as complex analysis, harmonic analysis, and algebraic geometry. Transcendental number theory. Transcendental number theory is a branch of number theory that studies transcendental numbers, which are numbers that are not roots of any non-zero polynomial equation with rational coefficients. Unlike algebraic numbers, transcendental numbers cannot be expressed as solutions to polynomial equations, making them fundamentally different and more complex. The theory explores properties, classifications, and methods to prove the transcendence of specific numbers. Key results include the proof that numbers such as e, the base of natural logarithms, and aa, pi, are transcendental. The field has deep connections with algebra, analysis, and logic, and it employs techniques from complex analysis, Diophantine approximation, and Galois theory. Transcendental number theory has significant implications in understanding the nature of numbers, the limitations of algebraic methods, and the structure of real and complex numbers. Additive number theory. Additive number theory is a branch of number theory that studies the properties of integers and their behavior under addition. It focuses on understanding how integers can be expressed as sums of other integers, often from specific subsets such as primes, squares, or other special sequences. Central problems include the Goldbach conjecture, which posits that every even integer greater than 2 can be expressed as the sum of two primes, and Waring's problem, which concerns representing natural numbers as sums of kth powers. Techniques in additive number theory often involve combinatorial methods, Fourier analysis, and the use of modular arithmetic. The field has deep connections to combinatorics, harmonic analysis, and algebra, and it plays a crucial role in understanding the additive structure of integers and related algebraic objects. Probabilistic number theory. Probabilistic number theory is a branch of number theory that applies probabilistic methods and ideas to study the distribution and properties of integers. It explores questions about the likelihood of certain number-theoretic events, such as the distribution of prime numbers, the behavior of arithmetic functions, and the occurrence of number patterns, by modeling these phenomena using probability theory. This approach often involves treating integers or their properties as random variables and analyzing their statistical behavior, which provides insights that complement classical deterministic methods. Key topics include the study of the distribution of prime numbers via probabilistic models, the Erdős Aycock theorem describing the normal distribution of the number of prime factors of integers, and the use of sieve methods and random models to understand multiplicative functions. Probabilistic number theory bridges the gap between pure number theory and probability, offering powerful tools to tackle complex problems in understanding the nature of integers. Computational number theory. Computational number theory is a branch of mathematics that focuses on the development and analysis of algorithms for solving problems related to integers and their properties. It combines concepts from number theory, which studies the properties of numbers such as divisibility, prime numbers, and congruences, with computational techniques to efficiently perform calculations and verify results. Key areas include integer factorization, primality testing, modular arithmetic, and cryptographic applications. This discipline plays a crucial role in modern cryptography, coding theory, and computer algebra systems, enabling practical solutions to problems that are otherwise difficult to handle analytically. Topology. Topology is a branch of mathematics concerned with the properties of space that are preserved under continuous transformations such as stretching, twisting, crumpling, and bending, but not tearing or gluing. It studies concepts like continuity, compactness, connectedness, and convergence. Fundamental objects in topology include topological spaces, which generalize the notion of geometric shapes, and continuous functions between these spaces. Key subfields include point-set topology, which deals with the foundational aspects of topology, algebraic topology, which uses tools from abstract algebra to study topological spaces, and differential topology, which focuses on differentiable functions on differentiable manifolds. Topology has applications across mathematics and science, including analysis, geometry, and physics. General topology. General topology, also known as point-set topology, is a fundamental branch of mathematics that deals with the study of topological spaces and continuous functions. It provides the basic language and framework for much of modern mathematics, including analysis, geometry, and algebra. The subject focuses on concepts such as open and closed sets, neighborhoods, bases, subbases, continuity, convergence, compactness, connectedness, and separation axioms. These concepts allow mathematicians to rigorously define and analyze the properties of spaces that are invariant under continuous deformations. General topology serves as the foundation for more specialized areas like algebraic topology and differential topology, and it is essential for understanding the structure and behavior of spaces in both pure and applied mathematics. Algebraic topology. Algebraic topology is a branch of mathematics that uses tools from abstract algebra to study topological spaces. The main goal is to find algebraic invariants that classify topological spaces up to homeomorphism, though often up to homotopy equivalence. Key concepts include homotopy, homology, and cohomology theories, which assign algebraic objects such as groups or rings to spaces in a way that reflects their topological structure. Fundamental groups capture information about loops in a space, while homology and cohomology groups provide information about higher dimensional wholes. These invariants help mathematicians understand complex spaces by translating geometric problems into algebraic ones, facilitating classification, comparison, and analysis of spaces in a rigorous manner. Differential topology. Differential topology is a branch of mathematics that deals with differentiable functions on differentiable manifolds. It studies the properties and structures that require only smoothness rather than a metric, focusing on concepts such as smooth manifolds, tangent spaces, vector fields, differential forms, and smooth maps. Key topics include the classification of manifolds, transversality, intersection theory, and Morse theory. Differential topology provides tools to understand how manifolds can be deformed and how their differentiable structures behave under continuous transformations, playing a crucial role in areas like geometry, dynamical systems, and theoretical physics. Geometric topology. Geometric topology is a branch of mathematics that studies manifolds and maps between them, focusing on properties that are preserved through continuous deformations, such as stretching and bending, but not tearing or gluing. It combines techniques from topology, geometry, and algebra to understand the structure and classification of spaces, particularly in low dimensions, such as 2, 3, and 4 dimensions. Key topics include the study of knots, three-manifolds, and surfaces, as well as the use of invariants like homotopy and homology groups, and geometric structures such as hyperbolic geometry. Geometric topology plays a crucial role in understanding the shape and behavior of spaces arising in both pure mathematics and theoretical physics. Low-dimensional topology. Low-dimensional topology is a branch of topology that focuses on the study of manifolds and spaces of 4 or fewer dimensions, particularly dimensions 2, 3, and 4. It involves understanding the properties and structures of these spaces that are invariant under continuous deformations, such as stretching or bending, but not tearing or gluing. Key objects of study include surfaces, two-dimensional manifolds, three manifolds, and four manifolds, with special attention to knots and links in three-dimensional space. This field combines techniques from algebraic topology, geometric topology, and differential topology, and has deep connections with other areas such as geometric group theory, quantum topology, and mathematical physics. Important concepts include the classification of surfaces, the study of three-manifold invariants like the fundamental group and Heegard splittings, knot theory, and the use of gauge theory and Floer homology in 4 dimensions. Low-dimensional topology has led to significant breakthroughs, including the proof of the Poincare conjecture in dimension 3 and advances in understanding smooth structures on 4 manifolds. Set-theoretic topology. Set-theoretic topology is a branch of topology that uses methods and concepts from set theory to study topological spaces and their properties. It focuses on the interplay between set-theoretic axioms, such as the axiom of choice and continuum hypothesis, and topological concepts like compactness, connectedness, and separability. This field investigates how different set-theoretic assumptions influence the structure and classification of topological spaces, often dealing with infinite and complex constructions. Key topics include the study of special types of spaces, such as metric spaces, compact spaces, and various separation axioms, as well as cardinal functions that measure the size and complexity of topological spaces. Set-theoretic topology provides deep insights into the foundations of topology and helps in understanding the limitations and possibilities within different mathematical frameworks. Topological data analysis. Topological data analysis, TDA, is an emerging field at the intersection of mathematics and data science that applies concepts from topology to analyze the shape and structure of data. Unlike traditional statistical methods, TDA focuses on the intrinsic geometric and topological features of data sets, such as connected components, holes, and voids, which are invariant under continuous transformations. The core tools of TDA include persistent homology, which studies the multi-scale topological features of data by examining how these features appear and disappear across different spatial resolutions, and mapper algorithms, which provide simplified representations of high-dimensional data. By capturing the underlying topological patterns, TDA enables robust analysis of complex, noisy, and high-dimensional data, making it valuable in various applications such as biology, sensor networks, image analysis, and machine learning. The discipline builds upon foundational concepts in algebraic topology, metric geometry, and computational topology, integrating them with algorithmic and statistical techniques to extract meaningful insights from data. Point-set topology. Point-set topology, also known as general topology, is the branch of topology that deals with the basic, set-theoretic definitions and constructions used in topology. It focuses on the concepts of open and closed sets, continuity, convergence, compactness, connectedness, and various separation axioms within topological spaces. A topological space is a set equipped with a collection of open subsets that satisfy certain axioms. The union of any collection of open sets is open. The finite intersection of open sets is open, and the set itself and the empty set are open. Point-set topology provides the foundational language and tools for more advanced areas of topology and analysis, allowing mathematicians to rigorously study the properties of spaces and functions between them without relying on notions of distance. Key concepts include neighborhood systems, bases and subbases for topologies, limit points, closure and interior of sets, continuous functions defined via pre-images of open sets, homeomorphisms as isomorphisms in topology, and various types of compactness such as sequential and countable compactness. This discipline is fundamental for understanding the structure and behavior of spaces in mathematics and has applications in many other fields, such as analysis, geometry, and mathematical physics. Continuum theory. Continuum theory is a branch of topology that focuses on the study of continua, which are compact, connected metric spaces. These spaces are fundamental objects in topology because they generalize the notion of continuous curves and surfaces without breaks or gaps. Continuum theory investigates properties such as connectedness, compactness, and dimensionality, and explores various types of continua, including dendrites, arcs, and indecomposable continua. The field also examines mappings between continua, decompositions, and the structure of subcontinua. Continuum theory has applications in dynamical systems, geometric topology, and analysis, providing insights into how complex structures can be understood through their continuous properties. Mathematical logic. Mathematical logic is a subfield of mathematics exploring formal systems in relation to the way we reason. It involves the study of syntax, semantics, and proof theory of formal languages used to represent mathematical statements and arguments. Key areas include propositional logic, which deals with logical connectives and truth values; predicate logic, which extends propositional logic by incorporating quantifiers and variables; model theory, which studies the interpretation of formal languages and structures; proof theory, focusing on the nature of mathematical proofs and formal deduction systems; and computability theory, which investigates what can be algorithmically computed. Mathematical logic provides foundational tools for mathematics, computer science, and philosophy, enabling rigorous analysis of mathematical reasoning, consistency, completeness, and decidability of formal systems. Propositional logic. Propositional logic, also known as sentential logic or statement logic, is a branch of mathematical logic that studies ways of joining and or modifying entire propositions, statements, or sentences to form more complex propositions. It deals with propositions that can be either true or false and uses logical connectives such as and, as, or, not, implies, we, and if and only if, or to build compound statements. The fundamental elements in propositional logic are propositional variables, which represent basic statements, and logical connectives that combine these variables. The truth value of compound propositions depends on the truth values of their components and the nature of the connectives. Propositional logic is foundational for reasoning in mathematics, computer science, and philosophy, providing tools for formal proof systems, automated theorem proving, and digital circuit design. It introduces concepts such as logical equivalence, tautologies, contradictions, satisfiability, and inference rules, which are essential for understanding more advanced logical systems. Predicate logic. Predicate logic, also known as first-order logic, is a formal system in mathematical logic that extends propositional logic by incorporating quantifiers and predicates. Unlike propositional logic, which deals with simple, declarative propositions that are either true or false, predicate logic allows for the expression of statements involving objects and their properties or relations. The key components of predicate logic include variables, predicates, which represent properties or relations, quantifiers, such as the universal quantifier, RTE meaning for all, and the existential quantifier, AE meaning there exists, logical connectives, and or not implies, and constants. This system enables the formulation of more complex and expressive statements about mathematical structures, facilitating rigorous reasoning about elements within a domain. Predicate logic forms the foundation for much of modern mathematics, computer science, and philosophy, particularly in areas such as model theory, proof theory, and automated theorem proving. Modal logic. Modal logic is a branch of mathematical logic that extends classical propositional and predicate logic to include operators expressing modality. Modality refers to concepts like necessity, possibility, knowledge, belief, and time. The primary modal operators are typically represented as non-DEG, necessity, and OOA, possibility. Modal logic provides a formal framework to reason about statements that are not only true or false, but also necessarily or possibly true. It has applications in philosophy, computer science, linguistics, and artificial intelligence, particularly in areas such as verification, knowledge representation, and reasoning about actions and beliefs. The semantics of modal logic is often given by Kripke models, which consist of a set of possible worlds and accessibility relations between them, allowing the interpretation of modal operators in terms of truth across these worlds. Various systems of modal logic exist, characterized by different axioms and rules governing the accessibility relations, enabling the study of different modalities such as temporal, epistemic, deontic, and dynamic modalities. Proof theory. Proof theory is a branch of mathematical logic that focuses on the study of formal proofs as mathematical objects. It analyzes the structure, properties, and transformations of proofs within formal systems, aiming to understand the nature of mathematical reasoning. Central to proof theory are concepts such as formal languages, inference rules, axioms, and proof calculi like natural deduction, sequent calculus, and Hilbert systems. Proof theory investigates consistency, completeness, and decidability of logical systems, and explores methods like cut elimination and normalization to simplify proofs. It also connects to computational aspects through the Curry-Howard correspondence, linking proofs with programs. Overall, proof theory provides foundational insights into the mechanics of deduction and the formalization of mathematics. Model theory. Model theory is a branch of mathematical logic that deals with the relationship between formal languages and their interpretations, or models. It studies the ways in which mathematical structures can satisfy the sentences of a given formal language, focusing on the properties of these structures and the expressiveness of the languages. Central concepts in model theory include structures, models, languages, theories, sets of sentences, satisfiability, elementary embeddings, and types. Model theory provides tools to analyze the consistency, completeness, and categoricity of theories, and it has applications in algebra, number theory, and computer science. It bridges syntax, formal languages and proofs, and semantics, models and truth, enabling a deep understanding of the foundations of mathematics. Set theory. Set theory is a fundamental branch of mathematical logic that studies sets, which are collections of objects considered as objects in their own right. It provides the basic language and framework for much of modern mathematics. The theory begins with the concept of a set, defined as a well-defined collection of distinct elements or members. Fundamental operations on sets include union, intersection, difference, and complement, which allow the construction of new sets from existing ones. Key concepts include subsets, power sets, the set of all subsets of a given set, Cartesian products, and relations. Set theory also explores infinite sets and introduces different sizes or cardinalities of infinity, such as countable and uncountable sets. Foundational axioms, such as those in Zermelo-Fraenkel's set theory, with the axiom of choice, ZFC, provide a rigorous basis for avoiding paradoxes and inconsistencies. Set theory underpins various areas of mathematics by formalizing the notion of collections and enabling precise definitions and proofs. Recursion theory. Recursion theory, also known as computability theory, is a branch of mathematical logic and computer science that studies the capabilities and limitations of algorithms and effective procedures. It focuses on classifying problems based on their solvability by mechanical means, typically using models such as Turing machines, lambda calculus, and recursive functions. The theory explores concepts like decidability, where a problem can be algorithmically solved, and undecidability, where no such algorithm exists. Key topics include the hierarchy of recursive and recursively enumerable sets, the halting problem, reductions between problems, and degrees of unsolvability. Recursion theory provides foundational insights into what can be computed in principle and forms the theoretical underpinning for computer science, particularly in understanding algorithmic complexity and the limits of automated reasoning. Computability theory. Computability theory, also known as recursion theory, is a branch of mathematical logic and computer science that studies the capabilities and limitations of algorithms and computational processes. It focuses on determining which problems can be solved by mechanical procedures or algorithms, and which cannot. Central to this theory are concepts such as Turing machines, which provide a formal model of computation, and recursive functions, which characterize computable functions. The theory explores decidability, which concerns whether there exists an algorithm to decide membership in a set, and undecidability, where no such algorithm exists. It also investigates degrees of unsolvability, classifying problems based on their relative computational complexity. Computability theory lays the foundational framework for understanding what can be computed in principle, influencing areas such as complexity theory, algorithm design, and the philosophy of mathematics. Automated theorem proving. Automated theorem proving, ATP, is a subfield of mathematical logic and computer science focused on the development of computer programs that prove mathematical theorems automatically. It involves the use of algorithms and formal methods to verify the validity of logical statements without human intervention. ATP systems typically represent mathematical statements in formal languages, such as first-order logic or higher-order logic, and apply inference rules to derive conclusions from axioms and previously established theorems. The field combines techniques from logic, artificial intelligence, and formal methods to address problems such as proof search, proof verification, and proof synthesis. Automated theorem proving has applications in verifying software and hardware correctness, formalizing mathematics, and aiding in mathematical discovery. Key approaches include resolution-based proving, term rewriting, and model checking. The discipline continues to evolve with advances in computational power and algorithm design, contributing significantly to both theoretical and practical aspects of mathematics and computer science. Non-classical logics. Non-classical logics are systems of logic that deviate from or extend classical logic in various ways to address limitations or to better capture certain types of reasoning. Unlike classical logic, which is bivalent and adheres strictly to the law of excluded middle and the law of non-contradiction, non-classical logics may relax or reject these principles to accommodate phenomena such as uncertainty, vagueness, inconsistency, or modality. Examples include intuitionistic logic, which rejects the law of excluded middle to reflect constructive reasoning; modal logics, which introduce modalities like necessity and possibility; many-valued logics, which allow for more than two truth values; fuzzy logic, which deals with degrees of truth; relevance logic, which ensures the premises are relevant to the conclusion; and paraconsistent logic, which tolerates contradictions without triviality. These logics have applications in computer science, linguistics, philosophy, and artificial intelligence, providing frameworks for reasoning in contexts where classical logic is insufficient or inadequate. Discrete mathematics. Discrete mathematics is a branch of mathematics that deals with countable, distinct, and separate objects. Unlike continuous mathematics, which studies structures that can vary smoothly, discrete mathematics focuses on structures such as integers, graphs, and statements in logic that have distinct and separate values. Key areas within discrete mathematics include combinatorics, graph theory, logic, set theory, number theory, and algorithms. It provides the mathematical foundations for computer science, information theory, and cryptography by enabling the analysis and design of algorithms, data structures, and networks. Discrete mathematics is essential for understanding computational complexity, coding theory, and the formal verification of software and hardware systems. Its applications span from solving counting problems and optimizing networks to designing secure communication protocols and developing efficient algorithms for data processing. Combinatorics. Combinatorics is a branch of mathematics focused on the study of finite or countable discrete structures. It involves counting, arranging, and analyzing configurations of objects according to specified rules. Key areas within combinatorics include enumeration, counting the number of ways certain patterns can be formed; graph theory, studying networks of nodes and edges; design theory, arranging elements into patterns with specific properties; and combinatorial optimization, finding the best arrangement or selection under given constraints. Combinatorics has applications across computer science, probability, algebra, and geometry, providing foundational tools for problem-solving in discrete mathematics. It explores principles such as permutations, combinations, the pigeonhole principle, inclusion-exclusion, and generating functions, enabling rigorous analysis of complex discrete systems. Graph theory. Graph theory is a branch of discrete mathematics that studies graphs, which are mathematical structures used to model pairwise relations between objects. A graph consists of vertices, also called nodes, and edges, connections between pairs of vertices. Graphs can be directed or undirected, weighted or unweighted, and may contain cycles or be acyclic. Key concepts in graph theory include paths, cycles, connectivity, trees, bipartite graphs, planar graphs, and graph coloring. Applications of graph theory span computer science, biology, social sciences, and logistics, where it is used to model networks, optimize routes, analyze relationships, and solve problems related to connectivity and flow. The discipline provides foundational tools for algorithms and combinatorics, enabling the analysis and solution of complex problems involving discrete structures. Logic. Logic is a fundamental branch of mathematics and philosophy that deals with the principles of valid reasoning and inference. In the context of discrete mathematics, logic provides the formal framework for analyzing statements, constructing proofs, and designing algorithms. It involves the study of propositions, which are declarative statements that can be either true or false, and logical connectives such as and, or, not, implies, and if and only if, which combine propositions to form more complex statements. Key concepts include truth tables, which systematically enumerate the truth values of compound statements; logical equivalences, which identify statements that have the same truth value in all cases; predicates and quantifiers, which extend propositional logic to express properties of objects and their relationships; and inference rules, which govern the derivation of conclusions from premises. Logic underpins many areas of computer science, including programming language semantics, automated theorem proving, and artificial intelligence, making it an essential topic within discrete mathematics. Set theory. Set theory is a fundamental branch of mathematics that studies collections of objects, known as sets. It provides the basic language and framework for most of modern mathematics. In set theory, a set is defined as a well-defined collection of distinct elements or members. Key concepts include elements, subsets, unions, intersections, complements, and Cartesian products. The theory also explores relations and functions between sets. Set theory introduces important principles, such as the axiom of choice and the concept of cardinality, which measures the size of sets, including infinite sets. It serves as the foundation for topics in discrete mathematics, logic, and computer science, enabling rigorous reasoning about collections and their properties. Number theory. Number theory is a branch of pure mathematics devoted primarily to the study of the integers and integer-valued functions. It explores properties and relationships of numbers, especially the positive integers. Key topics include divisibility, prime numbers, greatest common divisors, modular arithmetic, Diophantine equations, and the distribution of primes. Number theory has both theoretical significance and practical applications in cryptography, computer science, and coding theory. It is foundational within discrete mathematics, focusing on discrete rather than continuous structures, and forms an essential part of mathematical research and education. Algorithms. Algorithms are step-by-step procedures or formulas for solving problems, especially by a computer. In the context of mathematics, particularly discrete mathematics, algorithms are fundamental for processing data, performing calculations, and automating reasoning tasks. They consist of a finite sequence of well-defined instructions that take an input and produce an output after a finite number of steps. Algorithms are analyzed based on their correctness, efficiency, time and space complexity, and scalability. Key concepts include sorting, searching, graph algorithms, dynamic programming, and complexity classes. Understanding algorithms is crucial for designing efficient computational methods and for theoretical insights into problem-solving capabilities. Cryptography. Cryptography is a branch of mathematics and computer science focused on securing communication and data through the use of codes and ciphers. It involves the study of techniques for encrypting information to protect it from unauthorized access, ensuring confidentiality, integrity, authentication, and non-repudiation. Within discrete mathematics, cryptography relies heavily on number theory, combinatorics, and algebraic structures such as groups, rings, and fields. Key concepts include symmetric key cryptography, where the same key is used for both encryption and decryption, and asymmetric key cryptography, which uses a pair of keys, public and private, for secure communication. Cryptographic protocols also employ hash functions, digital signatures, and random number generation to enhance security. The mathematical rigor behind cryptography ensures that algorithms are resistant to attacks and can provide provable security guarantees under certain computational hardness assumptions. Automata theory. Automata theory is a fundamental area of theoretical computer science and discrete mathematics that deals with the study of abstract machines, or automata, and the computational problems that can be solved using these machines. It provides a formal framework for understanding how machines compute functions and recognize patterns, which is essential for the design and analysis of algorithms, programming languages, and compilers. The theory encompasses various types of automata, including finite automata, push-down automata, and Turing machines, each with increasing computational power. Finite automata are used to model and analyze regular languages, which are the simplest class of languages recognizable by machines. Push-down automata extend this capability to context-free languages by incorporating a stack memory, enabling the modeling of more complex structures like nested parentheses in programming languages. Turing machines represent the most powerful class of automata, capable of simulating any algorithmic process and serving as a foundational model for computability and complexity theory. Automata theory also explores the relationships between different classes of languages and automata, closure properties, decision problems, and the limits of computation. It plays a crucial role in various applications such as lexical analysis, pattern matching, artificial intelligence, and the development of formal verification methods for software and hardware systems. Coding theory. Coding theory is a branch of mathematics and computer science that focuses on the design and analysis of codes used for reliable data transmission and storage. It involves creating algorithms and mathematical structures that enable the detection and correction of errors introduced during the communication process. The field encompasses various types of codes, including linear codes, cyclic codes, and convolutional codes, each with specific properties and applications. Key concepts in coding theory include encoding, decoding, error detection, error correction, Hamming distance, and code rate. The discipline plays a crucial role in digital communications, data compression, cryptography, and information theory, ensuring data integrity and efficiency in systems ranging from satellite communication to data storage devices. Discrete probability. Discrete probability is a branch of probability theory that deals with discrete sample spaces, where the set of possible outcomes is countable, often finite or countably infinite. It involves assigning probabilities to individual outcomes or events within these discrete spaces, ensuring that the sum of probabilities of all possible outcomes equals 1. Key concepts include probability mass functions, PMFS, which specify the probability of each outcome, cumulative distribution functions, CDFS, which give the probability that a random variable is less than or equal to a certain value, and expectation, variance, and other moments that describe the distribution's characteristics. Discrete probability is foundational in modeling and analyzing random processes in computer science, combinatorics, and various applied fields, where events occur in distinct separate steps or states. Mathematical induction. Mathematical induction is a fundamental proof technique used in mathematics, particularly in discrete mathematics, to establish the truth of an infinite sequence of statements. It is especially useful for proving propositions indexed by natural numbers. The process involves two main steps: the base case and the inductive step. First, the base case verifies that the statement holds for the initial value, usually n equals 0 or n equals 1. Next, the inductive step assumes that the statement holds for some arbitrary natural number k, the induction hypothesis, and then proves that the statement must also hold for k plus 1. By successfully completing these steps, one concludes that the statement is true for all natural numbers, starting from the base case. Mathematical induction is closely related to the well-ordering principle and is a cornerstone in proofs involving sequences, sums, inequalities, and algorithm correctness in discrete mathematics. Recurrence relations. Recurrence relations are equations that define sequences recursively. Each term is expressed as a function of its preceding terms. They are fundamental in discrete mathematics for modeling and solving problems involving sequences and iterative processes. A common example is the Fibonacci sequence, where each term is the sum of the two preceding ones. Solving recurrence relations involves finding a closed-form expression that allows direct computation of any term without referring to previous terms. Techniques for solving them include iteration, characteristic equations, generating functions, and the use of the master theorem for divide and conquer recurrences. Recurrence relations are widely used in algorithm analysis, combinatorics, and computer science to describe the time complexity of recursive algorithms and to model discrete dynamic systems. Differential equations. Differential equations are mathematical equations that relate a function with its derivatives. They play a crucial role in modeling various physical, biological, and economic systems where change is involved. The study of differential equations involves finding functions that satisfy these equations, which can describe phenomena such as motion, heat transfer, population dynamics, and electrical circuits. There are two main types: ordinary differential equations, ODEs, which involve functions of a single variable and their derivatives, and partial differential equations, PDEs, which involve functions of multiple variables and their partial derivatives. Solutions to differential equations can be explicit or implicit and may require analytical or numerical methods. Key concepts include initial and boundary conditions, linearity, order, and homogeneity. Understanding differential equations is fundamental for advancing in applied mathematics, physics, engineering, and many other scientific disciplines. Ordinary differential equations, ODEs. Ordinary differential equations, ODEs are equations involving functions of a single independent variable and their derivatives. They describe the relationship between a function and its rates of change, and are fundamental in modeling various physical, biological, and engineering systems. An ODE can be expressed in the form f of x, y, y prime, y double prime, dot, 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 y to the power of n equals 0, where y is the dependent variable, x is the independent variable, and y prime, y double prime. Y to the power of n denote derivatives of y with respect to x. Solutions to ODEs are functions that satisfy the equation, and methods to solve them include analytical techniques such as separation of variables, integrating factors, characteristic equations for linear ODEs, and qualitative approaches like phase plane analysis. ODS are classified by order, the highest derivative present, linearity, linear or nonlinear, and homogeneity. Understanding ODEs is crucial for predicting system behavior over time and forms the basis for more advanced topics like partial differential equations and dynamical systems. Partial differential equations, PDEs. Partial differential equations, PDEs, are mathematical equations that involve functions of several variables and their partial derivatives. They are fundamental in describing a wide range of phenomena in physics, engineering, and other sciences, such as heat conduction, wave propagation, fluid dynamics, and quantum mechanics. PDEs are classified based on their order, linearity, and the nature of their solutions into types like elliptic, parabolic, and hyperbolic equations. Solving PDEs often requires specialized analytical methods, such as separation of variables, transform methods, and Green's functions, as well as numerical techniques like finite difference, finite element, and spectral methods. Understanding PDEs involves studying their formulation, properties, and solution techniques, which are essential for modeling and analyzing complex systems governed by continuous variables. Systems of differential equations. Systems of differential equations involve multiple interrelated differential equations that describe the behavior of several dependent variables with respect to one or more independent variables. Unlike a single differential equation, a system captures the dynamics of complex phenomena where variables influence each other. Typically, these systems can be expressed in vector form as x prime of t equals f of t, x of t, where x of t is a vector of functions and f is a vector-valued function. Solutions to these systems provide insights into the evolution of the entire system over time or space. Methods for solving systems include analytical techniques such as eigenvalue and eigenvector analysis for linear systems, phase plane analysis, and qualitative methods, as well as numerical approaches like Euler's method and Runge-Kutta methods for nonlinear or complex systems. Systems of differential equations are fundamental in modeling real-world phenomena in physics, biology, engineering, and economics, where multiple quantities interact dynamically. Nonlinear differential equations. Nonlinear differential equations are equations involving unknown functions and their derivatives, where the dependence on the unknown function or its derivatives is nonlinear. Unlike linear differential equations, nonlinear equations cannot generally be solved using superposition principles, making their analysis and solutions more complex. These equations arise in various fields such as physics, biology, engineering, and economics to model phenomena like population dynamics, fluid flow, chemical reactions, and mechanical systems with nonlinear behavior. Key characteristics of nonlinear differential equations include the possibility of multiple equilibrium points, limit cycles, chaos, and bifurcations. Analytical solutions are rare, so qualitative methods, numerical simulations, and perturbation techniques are often employed to study their behavior. Understanding nonlinear differential equations is crucial for predicting and controlling complex systems where linear approximations fail. Linear differential equations. Linear differential equations are a class of differential equations characterized by the linearity of the unknown function and its derivatives. Specifically, a linear differential equation can be expressed in the form a sub n of xd to the power of ny over dx to the power of n plus a sub n minus 1 of xd to the power of n minus 1y over dx to the power of n minus 1 plus a sub 1 of xdry over dx plus a sub 0 of xy equals g of x, where y is the unknown function of the variable x. The coefficients ai of x are functions of x, which may be constants, and g of x is a given function representing the non-homogeneous term. If g of x equals 0, the equation is called homogeneous. Otherwise, it is non-homogeneous. The theory of linear differential equations is fundamental in mathematics and applied sciences because it provides methods to model and solve problems involving rates of change with linear dependencies. Solutions to linear differential equations can often be found using techniques such as the method of undetermined coefficients, variation of parameters, and the use of integrating factors. The principle of superposition applies to homogeneous linear differential equations, meaning that any linear combination of solutions is also a solution. This property greatly facilitates the construction of general solutions. Linear differential equations are categorized by their order, which is the highest derivative present, and by whether their coefficients are constant or variable. First-order linear differential equations have the general form dy over dx plus p of xy equals q of x, and can be solved using integrating factors. Higher-order linear differential equations may require characteristic equations and eigenvalue methods when coefficients are constant. Overall, linear differential equations form a crucial part of the broader study of differential equations, providing a structured framework for understanding dynamic systems in physics, engineering, economics, and beyond. Stochastic differential equations. Stochastic differential equations, SDES, are differential equations in which one or more terms are stochastic processes, leading to solutions that are themselves stochastic processes. Unlike ordinary differential equations, which model deterministic systems, SDEs incorporate randomness and are used to model systems influenced by noise or uncertainty. Mathematically, an SDE typically takes the form dxt equals f of xt, tdt plus g of xt, tdwt, where xt is the stochastic process of interest, f is the drift coefficient representing deterministic trends, g is the diffusion coefficient representing the intensity of randomness, and wt is a Wiener process or Brownian motion. SDEs are fundamental in various fields such as physics, biology, finance, and engineering for modeling phenomena like stock prices, particle diffusion, and population dynamics under random influences. The theory of SDEs involves concepts like its square root yen calculus, which extends classical calculus to stochastic integrals and differential equations, enabling rigorous analysis and solution methods. Key results include existence and uniqueness theorems for solutions, its lemma for stochastic calculus, and methods for numerical approximation such as the Euler-Maruyama scheme. Understanding SDEs requires a solid foundation in probability theory, measure theory, and classical differential equations. Delay. Differential equations. Delay. Differential equations, DDES, are a class of differential equations in which the derivative of the unknown function at a certain time depends not only on the value of the function at that time, but also on its values at previous times. This introduces a time delay or lag into the system, making the analysis and solution of these equations more complex than ordinary differential equations, ODEs. Mathematically, a typical DDE can be expressed as dy of t over dt equals f of t, y of t minus epsilon n, where epsilon n greater than 0 represents the delay. DDEs, are used to model various real-world phenomena where the current rate of change depends on past states, such as population dynamics, control systems, physiological processes, and engineering applications. The presence of delay can lead to rich and complex dynamics, including oscillations, stability switches, and bifurcations. Analytical solutions are often difficult to obtain, so numerical methods and qualitative analysis play a significant role in studying these equations. Understanding the stability and behavior of solutions to DDEs requires specialized techniques that extend those used for ODEs, including the use of characteristic equations, Laplace transforms, and Lyapunov functionals. Fractional differential equations. Fractional differential equations, FDES, are a generalization of classical differential equations where the derivatives are of non-integer, fractional order. Unlike ordinary derivatives that represent rates of change at an instant, fractional derivatives provide a powerful tool to describe memory and hereditary properties of various materials and processes. This is because fractional derivatives are defined via integral operators that account for the entire history of the function, making them suitable for modeling complex systems in physics, engineering, biology, and finance. The most common definitions of fractional derivatives include the Riemann-Liouville, Caputo, and Grunwald-Letnikov formulations, each with unique properties and applications. Solving FDEs often requires specialized analytical and numerical methods due to their non-local nature. Applications of fractional differential equations span anomalous diffusion, viscoelasticity, control theory, and signal processing, among others, making them a vital area of research in modern applied mathematics. Numerical methods for differential equations. Numerical methods for differential equations encompass a variety of algorithms and techniques used to approximate solutions to differential equations, which often cannot be solved analytically. These methods are essential in mathematics and applied sciences for modeling and simulating real-world phenomena described by ordinary differential equations, ODS, and partial differential equations, PDEs. Key approaches include finite difference methods, which approximate derivatives by differences, finite element methods, which break down complex domains into simpler parts for analysis, and spectral methods, which use global basis functions for high accuracy. Time-stepping schemes such as Euler's method, Runge-Kutta methods, and multi-step methods are commonly used for solving initial value problems. Stability, consistency, and convergence are critical properties analyzed to ensure the reliability of numerical solutions. Overall, numerical methods provide powerful tools to obtain approximate solutions where exact solutions are unattainable, enabling advances in engineering, physics, biology, and other fields. Qualitative theory of differential equations. The qualitative theory of differential equations is a branch of mathematics focused on understanding the behavior of differential equations without necessarily finding their explicit solutions. It involves analyzing the properties of solutions such as stability, periodicity, and asymptotic behavior by studying the structure of the equations and their phase space. This theory is particularly useful for nonlinear differential equations where closed-form solutions are often unavailable. Key concepts include equilibrium points, limit cycles, bifurcations, and invariant manifolds. Tools such as phase portraits, Lyapunov functions, and Poincaré maps are employed to visualize and characterize the dynamics of systems described by differential equations. The qualitative approach provides insights into the long-term behavior of dynamical systems, enabling predictions about system stability and response to perturbations, which are essential in fields like physics, biology, engineering, and economics. Linear algebra. Linear algebra is a branch of mathematics that deals with vector spaces and linear mappings between these spaces. It includes the study of lines, planes, and subspaces, but is also concerned with properties common to all vector spaces. Key concepts in linear algebra include vectors, matrices, determinants, eigenvalues, eigenvectors, and systems of linear equations. This discipline provides the foundational language and tools for many areas of mathematics and science, including physics, engineering, computer science, and economics. Linear algebra enables the representation and solution of linear systems, transformations, and the analysis of geometric structures in multi-dimensional spaces. Vector spaces. Vector spaces are fundamental structures in linear algebra, consisting of a set of vectors along with two operations, vector addition and scalar multiplication. These operations must satisfy 8 axioms, including associativity, commutativity of addition, existence of an additive identity, zero vector, existence of additive inverses, distributivity of scalar multiplication over vector addition and field addition, compatibility of scalar multiplication with field multiplication, and the existence of a multiplicative identity for scalar multiplication. Vector spaces can be defined over any field, such as the real numbers or complex numbers. They provide a framework for analyzing linear combinations, spans, linear independence, bases, and dimension. Examples include Euclidean spaces, function spaces, and solution sets of linear systems. Understanding vector spaces is crucial for studying linear transformations, eigenvalues, eigenvectors, and various applications across mathematics, physics, and engineering. Matrix theory. Matrix theory is a fundamental area within linear algebra that focuses on the study of matrices, which are rectangular arrays of numbers, symbols, or expressions arranged in rows and columns. This discipline explores various properties and operations involving matrices, such as addition, multiplication, inversion, and transposition. Key concepts include determinants, rank, eigenvalues, eigenvectors, and canonical forms like the Jordan normal form. Matrix theory is essential for solving systems of linear equations, performing linear transformations, and analyzing vector spaces. It also has applications across numerous fields, including computer science, physics, engineering, and statistics, where matrices serve as tools for modeling and computation. Linear transformations. Linear transformations are functions between vector spaces that preserve vector addition and scalar multiplication. Formally, a function t v to w between vector spaces v and w is a linear transformation if for any vectors u, v, and v and any scalar c, the following hold. T of u plus v equals t of u plus t of v, and t of cu equals ct of u. Linear transformations can be represented by matrices once bases for the vector spaces are chosen, allowing for concrete computations. They play a fundamental role in linear algebra as they generalize the concept of matrix multiplication and provide a framework for understanding geometric transformations, changes of basis, and the structure of vector spaces. Key properties include the kernel, set of vectors mapped to 0, image, set of vectors obtained as t of v for some v, rank, and nullity, which relate through the rank-nullity theorem. Understanding linear transformations is essential for applications in differential equations, computer graphics, optimization, and more. Eigenvalues and eigenvectors. In linear algebra, eigenvalues and eigenvectors are fundamental concepts associated with square matrices. Given a square matrix A, an eigenvector is a non-zero vector V, such that when A acts on V, the output is a scalar multiple of V. Mathematically, this is expressed as AV equals OAV, where OA is a scalar known as the eigenvalue corresponding to the eigenvector V. The eigenvalue OA represents the factor by which the eigenvector is scaled during the transformation represented by A. To find eigenvalues, one solves the characteristic equation determinant of A minus I equals 0, where I is the identity matrix of the same size as A. The solutions, I are the eigenvalues, and substituting each, I back into A minus IIV equals 0, yields the corresponding eigenvectors. Eigenvalues and eigenvectors have numerous applications, including diagonalization of matrices, stability analysis in differential equations, quantum mechanics, facial recognition algorithms, and principal component analysis in statistics. They provide insight into the properties of linear transformations, such as stretching, compressing, and rotating vectors in vector spaces. Inner product spaces. Inner product spaces are a fundamental concept in linear algebra and functional analysis, providing a way to introduce geometric notions such as length, angle, and orthogonality into vector spaces. Formally, an inner product space is a vector space V over a field, usually the real or complex numbers, equipped with an inner product which is a function Schlangle Schockstadt Archrangle V on times Va R2 Amath Ba F by ein, satisfying the following properties for all vectors U, V, W in V, and scalar alpha in F. 1. Conjugate symmetry U, V equals bar U, V. 2. Linearity in the first argument, alpha U plus W, V equals alpha U, V plus W, V. 3. Positive definiteness, V greater than or equal to 0 with equality, if and only if V equals 0. The inner product induces a norm defined by vertical bar, V, vertical bar equals square root of angle bracket, V, comma, V angle bracket, which allows measurement of vector lengths. Moreover, the concept of orthogonality arises naturally. Two vectors U and V are orthogonal if angle bracket U, V greater than or equal to 0. Inner product spaces generalize Euclidean spaces and are essential in many areas such as quantum mechanics, signal processing, and numerical analysis. They also provide the framework for defining orthonormal bases, projections, and the Gram-Schmidt process, which are crucial tools for decomposing and analyzing vectors in high-dimensional spaces. Orthogonality. Orthogonality is a fundamental concept in linear algebra that generalizes the notion of perpendicularity from Euclidean geometry to vector spaces. Two vectors are said to be orthogonal if their inner product, dot product in Euclidean space, is 0. This implies that they are at a right angle to each other in the geometric sense. Orthogonality extends beyond vectors to functions and more abstract mathematical objects through the use of inner product spaces. In an inner product space, orthogonality is defined by the inner product being 0, which allows for the generalization of geometric intuition to higher dimensions and more complex structures. Orthogonal vectors have important properties such as linear independence and the ability to form orthogonal bases, which simplify many computations, including projections and decompositions. Orthogonality is central to many applications in mathematics, physics, and engineering, including Fourier analysis, signal processing, and the solution of linear systems. Key concepts related to orthogonality include orthonormal sets, orthogonal vectors of unit length, orthogonal complements, and orthogonal projections. The Gram-Schmidt process is a standard method to construct an orthonormal basis from a given set of vectors. Overall, orthogonality provides a powerful framework for understanding and manipulating vector spaces and their subspaces. Diagonalization. Diagonalization is a process in linear algebra where a given square matrix is expressed as a product of three matrices, P, D, and P, where D is a diagonal matrix and P is an invertible matrix composed of the eigenvectors of the original matrix. This technique simplifies many matrix computations, such as finding powers of matrices and solving systems of linear differential equations. A matrix is diagonalizable if it has enough linearly independent eigenvectors to form the matrix P. The diagonal entries of D are the eigenvalues corresponding to these eigenvectors. Diagonalization is closely related to the spectral theorem, which states that every symmetric matrix can be diagonalized by an orthogonal matrix. This topic is fundamental in understanding linear transformations, eigenvalues, eigenvectors, and their applications in various fields, including physics, engineering, and computer science. Canonical forms. In linear algebra, canonical forms are standardized or simplified representations of matrices or linear transformations that reveal their essential structural properties. These forms facilitate understanding, classification, and computation by reducing complex objects to a more manageable and interpretable format. Common canonical forms include the Jordan canonical form, which decomposes a matrix into Jordan blocks corresponding to eigenvalues and generalized eigenvectors, highlighting the geometric and algebraic multiplicities of eigenvalues. Another important form is the diagonal canonical form, applicable when a matrix is diagonalizable, simplifying powers and functions of matrices. The rational canonical form provides a unique representation over a field without requiring eigenvalues, using invariant factors derived from the matrix's characteristic polynomial. These canonical forms are fundamental tools in solving systems of linear differential equations, analyzing linear operators, and studying similarity classes of matrices, thereby playing a crucial role in both theoretical and applied mathematics. Systems of linear equations. A system of linear equations is a collection of one or more linear equations involving the same set of variables. In mathematics, particularly in linear algebra, these systems are fundamental for modeling and solving problems where multiple linear relationships must be satisfied simultaneously. Each equation in the system represents a linear constraint, and the solution to the system is the set of variable values that satisfy all equations simultaneously. Systems of linear equations can be classified based on the number of equations and variables, and their solutions can be unique, infinite, or non-existent. Methods for solving these systems include substitution, elimination, matrix operations, such as Gaussian elimination, and using determinants via Cramer's rule. The study of these systems is crucial for understanding vector spaces, linear transformations, and matrix theory, and has applications across science, engineering, economics, and beyond. Determinants. In linear algebra, the determinant is a scalar value that can be computed from the elements of a square matrix and encodes important properties of the matrix. It provides critical information about the matrix, such as whether the matrix is invertible. A non-zero determinant indicates invertibility, the scaling factor of the linear transformation described by the matrix, and the volume distortion of geometric shapes under that transformation. The determinant of a 2x2 matrix ABCD is calculated as a D minus BC. For larger matrices, determinants are computed using recursive expansion by minors or more efficient methods like LU decomposition. Properties of determinants include multilinearity, alternation, swapping two rows changes the sign, and normalization. The determinant of the identity matrix is 1. Determinants also play a key role in solving systems of linear equations, Cramer's rule, finding eigenvalues, and in differential geometry and calculus for changing variables in integrals. Numerical linear algebra. Numerical linear algebra is a subfield of linear algebra that focuses on developing and analyzing algorithms for performing linear algebra computations on computers. It deals with the numerical solution of problems involving matrices and vectors, such as solving systems of linear equations, eigenvalue problems, and matrix factorizations. The discipline emphasizes the accuracy, stability, and efficiency of these algorithms, considering the limitations of finite precision arithmetic in digital computations. Key topics include LU decomposition, QR factorization, singular value decomposition, SVD, iterative methods for large sparse systems, and error analysis. Numerical linear algebra is fundamental in scientific computing, engineering, data analysis, and machine learning, where large-scale linear algebra problems frequently arise. Combinatorics. Combinatorics is a branch of mathematics focused on counting, arranging, and analyzing discrete structures. It involves studying finite or countable configurations, such as permutations, combinations, and partitions, to understand how objects can be selected or arranged under specific constraints. Key concepts include the principle of counting, binomial coefficients, the pigeonhole principle, inclusion-exclusion principle, and generating functions. Combinatorics has applications in diverse areas like probability theory, computer science, optimization, and algebra. It provides foundational tools for solving problems related to enumeration, graph theory, design theory, and coding theory, making it essential for both theoretical and applied mathematics. Enumerative combinatorics. Enumerative combinatorics is a branch of combinatorics focused on counting the number of ways certain patterns can be formed. It deals with the enumeration of combinatorial structures such as permutations, combinations, partitions, and graphs. The main goal is to find explicit formulas, generating functions or recurrence relations that describe the number of objects of a given size that satisfy specific properties. Techniques used in enumerative combinatorics include the principle of inclusion-exclusion, bijective proofs, generating functions, and the use of recurrence relations. This field has applications in computer science, probability, and algebra, providing foundational tools for analyzing discrete structures and algorithms. Graph theory. Graph theory is a branch of mathematics that studies the properties and applications of graphs, which are mathematical structures used to model pairwise relations between objects. A graph consists of vertices, also called nodes, connected by edges. Graph theory explores various types of graphs such as directed, undirected, weighted, and unweighted graphs, and investigates concepts like connectivity, paths, cycles, trees, and graph coloring. It has applications in computer science, biology, social sciences, and many other fields. Key topics include Eulerian and Hamiltonian paths, planar graphs, graph isomorphism, network flows, and graph algorithms. This discipline is a fundamental part of combinatorics and provides tools for solving problems related to networks, optimization, and discrete structures. Design theory. Design theory is a branch of combinatorics that focuses on the arrangement of elements within a set into specific patterns or configurations called designs. These designs are structured collections of subsets, known as blocks, which satisfy certain balance and symmetry properties. The primary goal is to ensure that each element or combination of elements appears in a controlled and uniform manner across the blocks. Common types of designs include balanced incomplete block designs, BIBDS, Steiner systems, and finite projective planes. Design theory has applications in experimental design, error-correcting codes, cryptography, and finite geometry. It combines algebraic, geometric, and combinatorial methods to study existence, construction, and classification of these designs. Combinatorial optimization. Combinatorial optimization is a subfield of mathematics and computer science that focuses on optimizing an objective function whose domain is a discrete but large configuration space. It involves finding an optimal object from a finite set of objects, often under certain constraints. Typical problems include finding the shortest path in a graph, the minimum spanning tree, the maximum matching, or the optimal assignment. These problems are fundamental in various applications such as logistics, network design, scheduling, and resource allocation. The field combines techniques from combinatorics, graph theory, linear programming, and algorithm design to develop efficient methods for solving these optimization problems, many of which are NP-hard, requiring approximation or heuristic approaches. Extremal combinatorics. Extremal combinatorics is a branch of combinatorics that studies the maximal or minimal size of a collection of finite objects that satisfies certain restrictions. It focuses on determining the largest or smallest possible structure that avoids a particular substructure or property. For example, a classic problem in extremal combinatorics is to find the maximum number of edges in a graph that does not contain a complete subgraph of a given size. This field encompasses various fundamental results and theorems, such as Tur square root degree n's theorem, the IRD approximately equals ES-AI Stone theorem, and the Seymour square root copyright die regularity lemma. Extremal combinatorics has applications in graph theory, number theory, computer science, and optimization, providing deep insights into the interplay between structure and size in discrete systems. Algebraic combinatorics. Algebraic combinatorics is a branch of mathematics that employs algebraic techniques to study combinatorial structures and problems. It explores the interplay between combinatorial objects, such as graphs, posés, and designs, and algebraic structures like groups, rings, and vector spaces. Key areas within algebraic combinatorics include the study of symmetric functions, representation theory of symmetric groups, association schemes, and the use of generating functions to count combinatorial objects. This discipline provides powerful tools to solve enumeration problems, analyze combinatorial identities, and understand the symmetry and structure underlying combinatorial configurations. It has applications in diverse fields such as coding theory, geometry, and theoretical computer science, making it a vital area of research within mathematics. Probabilistic combinatorics. Probabilistic combinatorics is a branch of mathematics that applies probability theory to combinatorial problems. It studies the behavior and properties of combinatorial structures when randomness is introduced, either by considering random objects or by analyzing deterministic objects using probabilistic methods. This field encompasses topics such as random graphs, random permutations, and probabilistic methods for proving existence theorems. Key techniques include the probabilistic method, which uses probability to demonstrate the existence of combinatorial configurations, and concentration inequalities, which provide bounds on the likelihood that a random variable deviates from its expected value. Probabilistic combinatorics has applications in computer science, statistical physics, and network theory, providing powerful tools to tackle problems that are difficult to solve using purely deterministic approaches. Combinatorial geometry. Combinatorial geometry is a branch of mathematics that studies combinatorial properties and constructive methods of discrete geometric objects. It focuses on the arrangement, combination, and intersection patterns of points, lines, polygons, and other geometric figures, often in Euclidean space. This field explores problems such as counting the number of distinct configurations, understanding the structure of geometric graphs, and analyzing properties like convexity, incidences, and coverings. Combinatorial geometry has applications in computer science, optimization, and discrete mathematics, and it intersects with topics like graph theory, computational geometry, and discrete topology. Key concepts include the study of arrangements of lines and hyperplanes, convex hulls, triangulations, and extremal problems related to distances and incidences among points and other geometric entities. Matroid theory. Matroid theory is a branch of combinatorics that generalizes the notion of linear independence in vector spaces to more abstract settings. A matroid is a combinatorial structure that captures and abstracts the essence of independence, allowing the study of independence properties in a wide variety of mathematical contexts such as graph theory, geometry, and optimization. Formally, a matroid M is defined as a pair, E, UIA, where E is a finite set called the ground set, and UIA is a collection of subsets of E, called independent sets, satisfying three axioms. 1. The empty set is independent. 2. Every subset of an independent set is independent. Hereditary property. 3. If one independent set is larger than another, there exists an element in the larger set that can be added to the smaller set to still form an independent set. Exchange property. These axioms abstract the properties of linear independence in vector spaces and acyclic subgraphs in graphs. Matroid theory provides a unified framework to study various combinatorial optimization problems, such as finding maximal independent sets, spanning trees, and greedy algorithms. It also connects to other mathematical areas like lattice theory, polyhedral combinatorics, and algebraic geometry. Key concepts in matroid theory include bases, maximal independent sets, circuits, minimal dependent sets, rank functions, closure operators, and dual matroids. The theory has important applications in algorithm design, network theory, and coding theory, making it a fundamental tool in discrete mathematics and theoretical computer science. Partition theory. Partition theory is a branch of combinatorics and number theory that studies the ways of expressing a positive integer as a sum of positive integers, without considering the order of the addends. Each such expression is called a partition of the integer. For example, the number 4 can be partitioned in 5 distinct ways: 4, 3 plus 1, 2 plus 2, 2 plus 1 plus 1, and 1 plus 1 plus 1 plus 1. Partition theory explores properties of partitions, generating functions, and their connections to other areas such as Q-series, modular forms, and representation theory. Key concepts include the partition function P of n, which counts the number of partitions of n, Ferrer's diagrams and Young tableau for visual representation, and various identities like Euler's partition identity and the Rogers-Ramanujan identities. The theory has applications in combinatorics, algebra, and mathematical physics. Mathematical analysis. Mathematical analysis is a branch of mathematics that focuses on the rigorous study of limits, continuity, differentiation, integration, and infinite series. It provides the foundational framework for understanding and formalizing concepts related to change and approximation, which are essential in many areas of mathematics and its applications. Within the broader discipline of mathematics, mathematical analysis builds upon algebraic and geometric principles to explore the behavior of functions and sequences in a precise and logical manner. It employs tools such as real and complex numbers, metric spaces, and topology to analyze convergence, continuity, and smoothness. This discipline is fundamental for advancing theoretical mathematics and for solving practical problems in physics, engineering, economics, and beyond, as it allows for the exact formulation and proof of properties related to continuous phenomena. Real analysis. Real analysis is a fundamental branch of mathematical analysis that focuses on the rigorous study of real numbers and real valued functions. Within the broader context of mathematical analysis, which deals with limits, continuity, differentiation, integration, and infinite series, real analysis provides the precise theoretical foundation for these concepts when restricted to the real number system. It explores properties such as convergence of sequences and series, continuity and differentiability of functions, the structure of the real number line, including completeness and order properties, and the Lebesgue theory of integration. By establishing rigorous proofs and definitions, real analysis ensures that the intuitive ideas of calculus and other analytical methods are mathematically sound and applicable to a wide range of problems in pure and applied mathematics. Complex analysis. Complex analysis is a branch of mathematical analysis that focuses on the study of functions of complex variables. While mathematical analysis broadly deals with limits, continuity, differentiation, integration, and infinite series primarily in real variables, complex analysis extends these concepts into the complex plane, where variables have both real and imaginary parts. This extension allows for the exploration of holomorphic functions, which are complex functions that are differentiable in a neighborhood of every point in their domain. Complex analysis provides powerful tools such as contour integration, Cauchy's integral theorem, and residue calculus, which have no direct analogues in real analysis. These tools enable the evaluation of complex integrals and the solution of problems in various areas, including fluid dynamics, electromagnetic theory, and number theory. The subject also studies conformal mappings, analytic continuation, and the behavior of singularities, enriching the broader framework of mathematical analysis by leveraging the unique properties of complex differentiation and integration. Functional analysis. Functional analysis is a branch of mathematical analysis that focuses on the study of vector spaces endowed with limit-related structures, such as norms, inner products, or topologies, and the linear operators acting upon these spaces. While mathematical analysis broadly deals with limits, continuity, differentiation, integration, and infinite series, functional analysis extends these concepts to infinite dimensional spaces, providing a framework to analyze functions as points in these spaces. It combines techniques from linear algebra and topology to study spaces of functions and their transformations, enabling the rigorous treatment of problems in differential equations, approximation theory, and quantum mechanics. Key objects of study include Banach and Hilbert spaces, bounded and unbounded operators, and spectral theory, all of which generalize finite-dimensional linear algebra concepts to infinite-dimensional contexts within the analytic framework. Measure theory. Measure theory is a fundamental branch of mathematical analysis that provides a rigorous framework for assigning a size or measure to subsets of a given space, extending the intuitive notions of length, area, and volume. Within mathematical analysis, which studies limits, continuity, and integration, measure theory formalizes the concept of integration beyond the classical Riemann integral, enabling the treatment of more complex functions and spaces. It introduces sigma algebras to define measurable sets and measures to quantify them, allowing the development of the Lebesgue integral. This integral is more powerful and flexible than the Riemann integral, as it can handle functions with many discontinuities and is essential in probability theory, functional analysis, and ergodic theory. Measure theory also underpins the rigorous study of convergence theorems, differentiation of measures, and provides tools for analyzing infinite dimensional spaces, making it a cornerstone of modern mathematical analysis. Integration theory. Integration theory is a fundamental branch within mathematical analysis that focuses on the rigorous study of integrals, extending the concept of summation of infinitesimal quantities beyond elementary calculus. While mathematical analysis broadly deals with limits, continuity, differentiation, and infinite series, integration theory specifically addresses the formulation, properties, and applications of integrals in a generalized and abstract framework. This includes the development of various integral definitions, such as the Riemann integral, which is suitable for many elementary functions, and the more powerful Lebesgue integral, which allows integration of a wider class of functions and provides better convergence properties. Integration theory also explores measure theory, which underpins the Lebesgue integral by providing a systematic way to assign sizes to sets, enabling integration over complex domains. Within mathematical analysis, integration theory serves as a bridge connecting differentiation and series with functional analysis and probability theory, offering tools to solve differential equations, analyze function spaces, and study stochastic processes. Its thorough understanding is essential for advancing in modern analysis and its applications in pure and applied mathematics. Fourier analysis. Fourier analysis is a branch of mathematical analysis that focuses on representing functions as sums or integrals of sinusoidal components, specifically sines and cosines. Within the broader context of mathematical analysis, which studies limits, continuity, differentiation, integration, and infinite series, Fourier analysis provides powerful tools for decomposing complex functions into simpler periodic elements. This decomposition facilitates the study of function properties, solving differential equations, and analyzing signals. The fundamental concept is the Fourier series, which expresses periodic functions as infinite sums of sine and cosine terms, and the Fourier transform, which generalizes this idea to non-periodic functions by representing them as integrals over continuous frequencies. Fourier analysis bridges pure and applied mathematics by enabling the examination of functions in both time and frequency domains, thus deepening the analytical understanding of function behavior within mathematical analysis. Harmonic analysis. Harmonic analysis is a branch of mathematical analysis that focuses on representing functions or signals as superpositions of basic waves, and studying the properties and transformations of these representations. Within the broader context of mathematical analysis, which deals with limits, continuity, differentiation, integration, and infinite series, harmonic analysis specifically investigates the decomposition of functions into fundamental oscillatory components, such as sines and cosines, through tools like the Fourier series and Fourier transform. This field extends the classical analysis of functions by emphasizing frequency content and spectral behavior, enabling the analysis of periodic and non-periodic phenomena. Harmonic analysis also explores generalizations involving abstract groups and spaces, providing a powerful framework for solving differential equations, signal processing, and understanding the structure of functions in various function spaces. Its techniques bridge pure and applied mathematics, enriching mathematical analysis by offering profound insights into the interplay between time or spatial domains and frequency domains. Calculus of variations. Calculus of variations is a branch of mathematical analysis that focuses on finding functions that optimize certain functionals, which are mappings from a space of functions to the real numbers. Unlike classical calculus, which deals with optimizing functions of finite dimensional variables, calculus of variations deals with infinite dimensional spaces and seeks to determine the function or functions that make a given integral expression attain a minimum or maximum value. This field is fundamental in understanding problems where the quantity to be optimized depends on an entire function rather than just discrete variables. Key concepts include the Euler-Lagrange equation, which provides necessary conditions for optimality, and methods to handle constraints and boundary conditions. Calculus of variations has profound applications in physics, engineering, and economics, particularly in areas such as mechanics, optics, and optimal control theory, where it helps to model and solve problems involving continuous systems within the rigorous framework of mathematical analysis. Differential equations. Differential equations, situated within the broader field of mathematical analysis, focus on equations involving derivatives of functions, which represent rates of change. Unlike general mathematical problems, differential equations specifically model how quantities evolve continuously over time or space, making them essential for describing dynamic systems. Within mathematical analysis, which rigorously studies limits, continuity, and functions, differential equations extend these concepts by exploring how functions behave under differentiation and integration. This topic encompasses both ordinary differential equations, ODEs, involving functions of a single variable, and partial differential equations, PDEs, involving multivariable functions. The study includes existence and uniqueness theorems, methods of solution, qualitative behavior, and stability analysis, all grounded in analytical techniques. Thus, differential equations serve as a bridge connecting abstract analytical theory with practical applications, enabling the precise formulation and solution of problems in physics, engineering, biology, and beyond. Metric spaces. Metric spaces are a fundamental concept within mathematical analysis, providing a rigorous framework to generalize notions of distance and convergence beyond the familiar Euclidean spaces. A metric space consists of a set equipped with a metric, a function that defines the distance between any 2 points in the set and satisfies properties such as non-negativity, identity of indiscernibles, symmetry, and the triangle inequality. This abstraction allows mathematicians to analyze continuity, limits, and convergence in a broad variety of contexts, including function spaces and more abstract structures. Within mathematical analysis, metric spaces serve as the foundational setting for studying sequences, series, and functions, enabling the extension of classical analytical concepts to more general and complex spaces. They also facilitate the exploration of completeness, compactness, and connectedness, which are crucial properties for understanding the behavior of functions and the structure of spaces in analysis. Topology in analysis. Topology in analysis is a subfield of mathematical analysis that focuses on the study of topological structures and their properties within analytical contexts. It provides a framework to rigorously define and analyze concepts such as convergence, continuity, compactness, and connectedness, which are fundamental in understanding the behavior of functions and sequences in various spaces. Unlike general topology, which studies abstract topological spaces, topology in analysis often deals with metric spaces, normed vector spaces, and more specialized structures like Banach and Hilbert spaces. This approach allows mathematicians to extend classical analysis results to more general settings, facilitating the study of limits, function spaces, and operators. By integrating topological concepts, mathematical analysis gains powerful tools to handle infinite dimensional spaces and complex function behaviors, thereby deepening the understanding of continuity, differentiability, and integrability in a more generalized and abstract framework. Numerical analysis. Numerical analysis is a specialized branch of mathematics that focuses on developing and analyzing algorithms to obtain approximate solutions to mathematical problems that are difficult or impossible to solve analytically. Within the broader field of mathematics, numerical analysis bridges theoretical concepts and practical computation by providing systematic methods for solving equations, performing integrations, differentiations, and optimizations, as well as handling large data sets and complex models. It addresses issues such as error estimation, stability, convergence, and computational efficiency, which are critical when applying mathematical techniques to real-world problems. By leveraging numerical methods, this discipline enables mathematicians and scientists to tackle problems in applied mathematics, physics, engineering, and computer science, where exact solutions are often unattainable or impractical. Root-finding algorithms. Root-finding algorithms are fundamental numerical methods within the field of numerical analysis, focused on identifying solutions to equations of the form f of x equals 0. These algorithms are essential because many mathematical problems reduce to finding roots of functions, which often cannot be solved analytically. Numerical analysis provides a framework for developing and analyzing these algorithms to ensure they are efficient, accurate, and stable. Common root-finding methods include bracketing methods like the bisection method, which guarantee convergence by repeatedly narrowing an interval containing a root. Open methods such as the Newton-Raphson method, which use derivatives to achieve rapid convergence but require good initial guesses. And hybrid methods that combine the robustness of bracketing with the speed of open methods. The study of root-finding algorithms involves understanding their convergence properties, error analysis, and computational complexity, all within the broader context of numerical approximation and algorithmic stability that numerical analysis addresses. Interpolation and approximation. Interpolation and approximation are fundamental techniques within numerical analysis focused on constructing new data points or functions based on a discrete set of known data. Interpolation involves finding a function, often a polynomial or spline, that exactly passes through a given set of data points. This is crucial when the goal is to estimate values within the range of the known data. Approximation, on the other hand, seeks to find a function that closely matches the data but does not necessarily pass through all points, often minimizing some error criterion. This is particularly useful when dealing with noisy data or when an exact fit is either impossible or undesirable. Both methods are essential for numerical solutions of problems where analytical expressions are unavailable or impractical. They enable efficient computation, data smoothing, and function reconstruction, serving as building blocks for more complex numerical algorithms such as numerical integration, differentiation, and solving differential equations. Within numerical analysis, interpolation and approximation provide systematic frameworks to balance accuracy, computational cost, and stability in numerical computations. Numerical integration and differentiation. Numerical integration and differentiation are fundamental techniques within numerical analysis, a branch of mathematics focused on developing and analyzing algorithms for approximating solutions to mathematical problems that cannot be solved analytically or where analytical solutions are impractical. Numerical integration involves approximating the value of definite integrals, especially when the integrand is complex, unknown in closed form, or when data is available only at discrete points. Common methods include the trapezoidal rule, Simpson's rule, and Gaussian quadrature, each balancing accuracy and computational efficiency. Numerical differentiation, on the other hand, approximates the derivative of a function based on discrete data points or function evaluations, often using finite difference formulas such as forward, backward, and central differences. Both processes are crucial in solving differential equations, optimization problems, and in simulations across science and engineering. Within numerical analysis, these techniques are studied not only for their practical implementation, but also for their error behavior, stability, and convergence properties, ensuring reliable and efficient computational methods. Numerical linear algebra. Numerical linear algebra is a specialized branch within numerical analysis that focuses on developing and analyzing algorithms for performing linear algebra computations with numerical data. While numerical analysis broadly addresses the design and study of methods for approximating solutions to mathematical problems, numerical linear algebra specifically deals with problems involving vectors and matrices, such as solving systems of linear equations, computing eigenvalues and eigenvectors, and performing matrix factorizations. This field is essential because many scientific and engineering problems can be formulated in terms of linear algebraic structures, but exact symbolic solutions are often infeasible for large-scale or complex systems. Numerical linear algebra provides stable, efficient, and accurate computational techniques that enable the practical solution of these problems on computers, taking into account issues like rounding errors, computational complexity, and convergence. It bridges theoretical linear algebra and applied numerical methods, ensuring that solutions to linear algebra problems are both mathematically sound and computationally feasible within the broader framework of numerical analysis. Numerical solutions of differential equations. Numerical solutions of differential equations is a specialized area within numerical analysis that focuses on developing and analyzing algorithms to approximate solutions of differential equations when closed-form analytical solutions are unavailable or difficult to obtain. Differential equations, which describe relationships involving rates of change and are fundamental in modeling physical, biological, and engineering systems, often cannot be solved exactly. Numerical analysis provides the theoretical foundation and computational techniques to discretize these equations and solve them approximately with controlled accuracy and stability. This topic encompasses methods such as finite difference, finite element, and spectral methods for partial differential equations, as well as Euler's method, Runge-Kutta methods, and multi-step methods for ordinary differential equations. It also involves error analysis, stability considerations, and convergence studies to ensure that the numerical solutions are reliable and efficient. By situating numerical solutions of differential equations within numerical analysis, the emphasis is on rigorous mathematical frameworks and algorithmic strategies that enable practical computation of solutions to complex differential models. Optimization methods. Optimization methods within the context of numerical analysis refer to a collection of mathematical techniques and algorithms designed to find the best solution or extremum, minimum, or maximum of a function subject to given constraints. Numerical analysis provides the tools to approximate solutions to optimization problems that are often too complex for analytical methods. These methods include Gradient-based algorithms, such as gradient descent and Newton's method, which use derivatives to iteratively approach optimal points. Derivative-free methods like the Nelder-Mead simplex algorithm, useful when derivatives are unavailable or expensive to compute. And constrained optimization techniques such as the method of Lagrange multipliers and interior point methods, which handle optimization problems with equality and inequality constraints. By leveraging numerical approximations, iterative procedures, and computational efficiency, optimization methods enable solving real-world problems in engineering, economics, machine learning, and scientific computing where exact solutions are impractical or impossible to obtain analytically. Error analysis and stability. Error analysis and stability are fundamental concepts within numerical analysis that focus on understanding and controlling the inaccuracies inherent in numerical computations. Error analysis involves identifying, quantifying, and managing different types of errors, such as round-off errors due to finite precision arithmetic and truncation errors arising from approximations in algorithms. Stability refers to how errors propagate through numerical methods. A stable algorithm ensures that errors do not grow uncontrollably as computations proceed. Together, these concepts help in designing and selecting numerical algorithms that produce reliable and accurate results, which is crucial because numerical methods approximate solutions to mathematical problems that often cannot be solved exactly. By analyzing error behavior and ensuring stability, numerical analysts can guarantee that computed solutions remain close to the true values, thereby making numerical methods robust and effective tools within the broader field of numerical analysis. Numerical methods for partial differential equations. Numerical methods for partial differential equations, PDEs, are specialized computational techniques developed within the broader field of numerical analysis to approximate solutions of PDEs, which are equations involving multivariable functions and their partial derivatives. Unlike ordinary differential equations, PDEs often model complex phenomena such as heat conduction, fluid flow, and electromagnetic fields, making analytical solutions rare or impossible. Numerical analysis provides the theoretical foundation for designing stable, accurate, and efficient algorithms to discretize and solve these equations. Common approaches include finite difference methods, which approximate derivatives by differences on a grid, finite element methods, which subdivide the domain into smaller elements and use variational principles, and spectral methods, which represent solutions in terms of global basis functions. Each method involves trade-offs in terms of convergence, computational cost, and applicability to different types of PDEs and boundary conditions. The study of numerical methods for PDEs within numerical analysis emphasizes error estimation, stability analysis, and convergence proofs to ensure that the computed solutions reliably approximate the true behavior of the modeled systems. Monte Carlo methods. Monte Carlo methods are a class of computational algorithms that rely on repeated random sampling to obtain numerical results. Within the context of numerical analysis, these methods are particularly valuable for solving problems that are deterministic in principle, but difficult or impossible to solve analytically or through traditional numerical techniques. Monte Carlo methods excel in high-dimensional integration, optimization, and simulation tasks by approximating solutions through probabilistic experiments. They are widely used to estimate integrals, solve partial differential equations, and model complex systems where uncertainty or stochastic processes play a significant role. The strength of Monte Carlo methods lies in their simplicity, flexibility, and ability to provide approximate solutions with quantifiable error bounds, making them an essential tool in the numerical analyst's toolkit for tackling problems that defy conventional deterministic approaches. Numerical methods for eigenvalue problems. Numerical methods for eigenvalue problems are specialized computational techniques within the broader field of numerical analysis, which focuses on developing and analyzing algorithms for approximating solutions to mathematical problems. Specifically, eigenvalue problems involve finding scalars, eigenvalues, and corresponding vectors, eigenvectors, such that when a linear transformation represented by a matrix is applied to an eigenvector, the output is a scalar, multiple of that vector. These problems are fundamental in various scientific and engineering applications, including stability analysis, vibration analysis, quantum mechanics, and more. Numerical analysis provides the theoretical foundation and practical algorithms to approximate eigenvalues and eigenvectors when exact analytical solutions are infeasible, especially for large or complex matrices. Key numerical methods include the power iteration, inverse iteration, QR algorithm, Jacobi method, and Arnoldi iteration, each with different convergence properties, computational complexities, and suitability depending on the matrix characteristics, for example, size, sparsity, symmetry. These methods are designed to balance accuracy, efficiency, and stability, addressing challenges such as sensitivity to perturbations and computational cost. Thus, numerical methods for eigenvalue problems represent a critical subfield of numerical analysis dedicated to solving one of the most important classes of linear algebra problems through reliable and efficient computational algorithms. Set theory. Set theory is a fundamental branch of mathematics that deals with the study of sets, which are well-defined collections of distinct objects considered as a whole. Within the broader discipline of mathematics, set theory provides the foundational language and framework for virtually all mathematical concepts and structures. It introduces basic notions such as membership, subsets, unions, intersections, and complements, enabling mathematicians to rigorously define and manipulate collections of elements. Set theory also explores more advanced topics like cardinality, which measures the size of sets, and ordinal numbers, which extend the concept of ordering. By formalizing these ideas, set theory underpins the logical structure of mathematics, allowing for the precise formulation of mathematical statements and proofs. Its principles are essential for understanding functions, relations, number systems, and more complex mathematical theories, making it an indispensable area within the field of mathematics. Basic set theory. Basic set theory is a foundational topic within the broader field of set theory, which itself is a fundamental branch of mathematics concerned with the study of sets or collections of distinct objects considered as a whole. Within the context of set theory, basic set theory introduces the essential concepts and operations that form the groundwork for more advanced topics. This includes the definition of a set, elements, subsets, and the ways to describe sets such as roster and set builder notation. It also covers fundamental operations like union, intersection, difference, and complement, as well as important properties and laws governing these operations, such as associativity, commutativity, distributivity, and De Morgan's laws. Additionally, basic set theory addresses the concepts of the empty set, universal set, and power set, and introduces relations such as membership and subset relations. Understanding these basics is crucial, as they underpin much of modern mathematics and logic, providing a language and framework for discussing collections of objects in a precise and structured way. By situating basic set theory within set theory, one appreciates how these elementary ideas serve as the building blocks for more complex structures and theories in mathematics. Axiomatic set theory. Axiomatic set theory is a branch of set theory that formalizes the concept of sets using a rigorous system of axioms. Unlike naive set theory, which allows unrestricted set formation and leads to paradoxes, such as Russell's paradox, axiomatic set theory establishes a foundation by specifying a collection of axioms that sets must satisfy. These axioms, such as those in the Zermelo-Fraenkel system, ZF, often augmented by the axiom of choice, ZFC, provide precise rules for set construction, membership, and operations, ensuring consistency and avoiding contradictions. Within the broader context of set theory, which studies the properties and relations of sets as fundamental mathematical objects, axiomatic set theory serves as the foundational framework that underpins modern mathematical reasoning and the formal development of mathematics itself. Descriptive set theory. Descriptive set theory is a branch of set theory that focuses on the study of definable sets, particularly subsets of Polish spaces, complete separable metric spaces, using tools from logic and topology. Unlike general set theory, which deals with arbitrary sets and their cardinalities, descriptive set theory investigates sets that can be described or classified through definability conditions, such as Borel, analytic, and projective sets. It explores the complexity and hierarchy of these sets, their structural properties, and the relationships between them. This field provides a framework for understanding how sets can be constructed or characterized using countable operations and continuous transformations, linking set-theoretic concepts with topological and measure-theoretic ideas. Within the broader context of set theory, descriptive set theory offers refined techniques to analyze sets that arise naturally in analysis and other areas of mathematics, emphasizing definability and classification over mere existence. Combinatorial set theory. Combinatorial set theory is a specialized branch of set theory that focuses on the study of combinatorial properties and structures within sets, particularly infinite sets. While set theory provides the foundational framework for understanding collections of objects and their relationships, combinatorial set theory delves deeper into the ways elements of sets can be arranged, partitioned, and combined, often employing techniques from combinatorics and logic. This field examines principles such as partition relations, cardinal characteristics, and infinite combinatorial principles like Ramsey theory and the use of large cardinals. It explores how these combinatorial aspects influence the structure and behavior of sets, especially infinite ones, thereby enriching the broader understanding of set theory by addressing intricate problems related to ordering, coloring, and selection within sets. Set-theoretic topology. Set-theoretic topology is a branch of topology that deeply integrates concepts and methods from set theory to study topological spaces and their properties. Within the context of set theory, it leverages the foundational understanding of sets, functions, and relations to rigorously define and analyze topological structures. This field focuses on how set-theoretic principles, such as cardinality, ordinals, and the axiom of choice influence the behavior and classification of topological spaces. It explores complex interactions between infinite sets and topological properties, including compactness, connectedness, and separability, often using advanced set-theoretic tools like forcing and large cardinals. By situating topology within the framework of set theory, set-theoretic topology provides a precise and foundational approach to understanding continuity, convergence, and other central topological concepts, highlighting the role of set-theoretic assumptions in shaping the landscape of topology. Infinite set theory. Infinite set theory is a specialized branch within set theory that focuses on the properties and behaviors of sets containing infinitely many elements. While set theory provides the foundational framework for understanding collections of objects, infinite set theory delves deeper into the nature of infinite sets, exploring concepts such as countability, uncountability, cardinality, and ordinal numbers. It distinguishes between different sizes or types of infinity. For example, the set of natural numbers is countably infinite, whereas the set of real numbers is uncountably infinite. This area also investigates operations and relations specific to infinite sets, including infinite unions and intersections, and the role of the axiom of choice in constructing and comparing infinite sets. By extending the principles of set theory to infinite contexts, Infinite set theory enables mathematicians to rigorously analyze and classify infinite collections, which are fundamental to many areas of mathematics and logic. Fuzzy set theory. Fuzzy set theory is an extension of classical set theory that deals with reasoning that is approximate rather than fixed and exact. While classical set theory defines membership of elements in a set in a binary manner, an element either belongs or does not belong to a set. Fuzzy set theory introduces the concept of partial membership. In this framework, each element has a membership degree ranging between 0 and 1, representing the extent to which the element belongs to the set. This allows for modeling uncertainty and vagueness inherent in many real-world situations where boundaries of sets are not sharply defined. Fuzzy sets are characterized by membership functions that assign to each element a membership value, enabling more flexible and nuanced classification compared to crisp sets. Thus, fuzzy set theory generalizes classical set theory by relaxing the strict membership criteria and providing tools to handle imprecise concepts, making it highly applicable in fields such as control systems, decision-making, and artificial intelligence. Applied set theory. Applied set theory is a specialized branch within set theory that focuses on the practical utilization of set-theoretic concepts, methods, and principles to solve real-world problems across various disciplines such as computer science, engineering, and economics. While set theory itself provides the foundational language and framework for understanding collections of objects, relations, and functions, applied set theory extends these abstract notions to model, analyze, and optimize complex systems. This includes the use of sets to represent data structures, the application of operations like unions, intersections, and complements to manipulate information, and the employment of advanced concepts such as cardinality and ordinals to address issues related to size and order. By grounding its techniques in the rigorous axioms and theorems of set theory, applied set theory ensures that practical problem-solving approaches maintain mathematical consistency and precision, bridging the gap between theoretical foundations and tangible applications. Graph theory. Graph theory is a branch of mathematics that studies graphs, which are mathematical structures used to model pairwise relations between objects. Within the broader discipline of mathematics, graph theory focuses on the properties and applications of graphs, which consist of vertices, also called nodes, connected by edges. This field explores various types of graphs, including directed and undirected graphs, weighted and unweighted graphs, and special classes such as trees, bipartite graphs, and planar graphs. Graph theory provides fundamental tools and concepts for analyzing connectivity, paths, cycles, and network flows, and it has significant applications in computer science, combinatorics, optimization, and many other areas of mathematics. By examining the structural and combinatorial aspects of graphs, graph theory contributes to a deeper understanding of discrete mathematical systems and their interrelations within the broader mathematical framework. Graph coloring. Graph coloring is a fundamental topic within graph theory that involves assigning colors to the elements of a graph subject to certain constraints. Typically, the most common form is vertex coloring, where each vertex of a graph is assigned a color such that no two adjacent vertices share the same color. This concept helps in understanding the structure and properties of graphs by analyzing how they can be partitioned or labeled. Graph coloring has important applications in scheduling, register allocation in compilers, frequency assignment, and solving puzzles like Sudoku. Within graph theory, it provides insights into graph invariants, such as the chromatic number, which is the minimum number of colors needed to achieve a proper coloring. The study of graph coloring also extends to edge coloring and face coloring in planar graphs, each with its own set of rules and applications. Overall, graph coloring serves as a crucial tool in exploring graph properties, optimizing resource allocation, and solving combinatorial problems inherent in the broader field of graph theory. Graph algorithms. Graph algorithms are a fundamental subset of graph theory, focusing on the development and analysis of algorithms to solve problems related to graphs. Within graph theory, which studies the properties and structures of graphs composed of vertices, nodes, and edges, connections, graph algorithms provide systematic methods to explore, traverse, and manipulate these graphs efficiently. These algorithms address a variety of tasks, such as finding the shortest path between nodes, for example, Dijkstra's and Bellman-Ford algorithms, detecting cycles, determining connectivity, computing minimum spanning trees, for example, Kruskal's and Prim's algorithms, and performing graph searches, for example, depth-first search and breadth-first search. By leveraging the theoretical foundations of graph theory, graph algorithms enable practical applications across computer science, network analysis, optimization, and many other fields, facilitating the solution of complex problems involving relational data structures. Planar graphs. Planar graphs are a fundamental concept within graph theory, focusing on graphs that can be embedded in the plane, such that no edges intersect except at their endpoints. This property distinguishes planar graphs from general graphs by imposing a geometric constraint that affects their structure and properties. In the context of graph theory, planar graphs are studied to understand how graph embeddings influence graph characteristics such as connectivity, coloring, and traversal. Key results related to planar graphs include Kuratowski's theorem, which characterizes planar graphs by forbidden subgraphs, and Euler's formula, which relates the number of vertices, edges, and faces in a planar embedding. Planar graphs have practical applications in network design, circuit layout, and geographic mapping, where avoiding edge crossings is crucial. Thus, within graph theory, planar graphs represent a specialized class that bridges combinatorial properties with geometric representation, enriching the study of graph embeddings and their implications. Random graphs. Random graphs is a subfield within graph theory that studies graphs generated by some random process. Unlike deterministic graphs, where the structure is fixed, random graphs are constructed by introducing randomness in the presence or absence of edges between vertices, often according to specified probability distributions. This approach allows mathematicians to analyze typical properties of graphs, such as connectivity, the emergence of giant components, degree distributions, and phase transitions under probabilistic models. The most classical model in this area is the Erdos-Renyi model, where each possible edge between a fixed set of vertices is included independently with a given probability. Random graphs provide insights into the behavior of large-scale networks and serve as a bridge between combinatorial graph theory and probability theory, enabling the study of average case scenarios and threshold phenomena within the broader context of graph theory. Graph connectivity. Graph connectivity is a fundamental concept within graph theory that deals with the ways in which vertices, nodes in a graph, are connected to each other. It examines whether there is a path between pairs of vertices and how robust these connections are under various conditions. In the context of graph theory, connectivity helps classify graphs into connected or disconnected types. A graph is connected if there exists at least one path between every pair of vertices. Otherwise, it is disconnected. Connectivity can be further analyzed through concepts such as connected components, which are maximal connected subgraphs. Additionally, the idea of K-connectivity measures the minimum number of vertices or edges that must be removed to disconnect the graph, providing insight into the graph's resilience. Understanding graph connectivity is crucial for applications such as network design, reliability analysis, and the study of social, biological, and communication networks within the broader framework of graph theory. Graph theory applications. Graph theory applications encompass the diverse ways in which the principles and structures studied within graph theory are utilized to solve practical problems across various fields. Building upon the foundational concepts of vertices, edges, connectivity, and graph properties explored in graph theory, These applications translate theoretical insights into real-world solutions. Examples include network design and analysis, where graphs model communication or transportation systems; scheduling problems, which use graph coloring to avoid conflicts; social network analysis, leveraging graph metrics to understand relationships and influence; and bioinformatics, where graphs represent molecular structures or genetic interactions. By applying the core ideas of graph theory, such as paths, cycles, trees, and flows, these applications demonstrate the discipline's power to model complex systems, optimize processes, and uncover hidden patterns, thereby bridging abstract theory and practical utility within the broader mathematical framework. Graph spectra. Graph spectra is a subfield within graph theory that focuses on the study of the eigenvalues and eigenvectors of matrices associated with graphs, such as the adjacency matrix, Laplacian matrix, and normalized Laplacian. These spectral properties provide deep insights into the structural characteristics of graphs, including connectivity, the presence of clusters or communities, expansion properties, and the behavior of random walks on graphs. By analyzing the spectrum of a graph, mathematicians can infer important combinatorial and topological features, solve optimization problems, and apply these results to various domains such as chemistry, physics, computer science, and network analysis. Graph spectra thus serves as a powerful bridge between algebraic methods and combinatorial graph properties, enriching the broader study of graph theory. Graph minors. Graph minors is a fundamental topic within graph theory that studies the properties and structures of graphs through the concept of minors. A graph minor is obtained by taking a graph and performing a series of operations: vertex deletions, edge deletions, and edge contractions. This concept allows mathematicians to analyze complex graphs by simplifying them into smaller, more manageable components while preserving certain structural characteristics. The theory of graph minors is crucial for understanding graph embeddings, graph structure theory, and has profound implications in algorithm design, particularly in solving problems that are otherwise computationally difficult. One of the landmark results in this area is the Robertson-Seymour theorem, which states that graphs are well quasi-ordered under the minor relation, leading to the conclusion that any minor closed family of graphs can be characterized by a finite set of forbidden minors. This has deep consequences in classifying graphs and designing efficient algorithms for graph problems constrained by these forbidden minors. Thus, within the broader field of graph theory, graph minors provides powerful tools and frameworks for dissecting and comprehending the intricate nature of graphs. Graph embeddings. Graph embeddings, within the context of graph theory, refer to the representation of graphs in a geometric or topological space, such that the vertices and edges are mapped to points and curves, respectively, in a way that preserves certain structural properties. Typically, an embedding of a graph is a drawing of the graph on a surface, such as the plane, a sphere, or more complex surfaces, where edges intersect only at their endpoints. This concept is fundamental in understanding planar graphs, which can be embedded in the plane without edge crossings, and extends to embeddings on surfaces of higher genus. Graph embeddings are crucial for visualizing graphs, analyzing their topological properties, and solving problems related to graph planarity, crossing numbers, and graph minors. They also play a significant role in algorithm design, particularly in graph drawing algorithms and in the study of graph isomorphisms and automorphisms within the framework of graph theory. Directed graphs. Directed graphs, also known as digraphs, are a fundamental concept within graph theory, a branch of mathematics that studies the properties and applications of graphs. Unlike undirected graphs, where edges have no orientation, directed graphs consist of vertices connected by edges that have a specific direction, indicated by arrows. This directionality means each edge goes from one vertex, the source, to another vertex, the target, which allows directed graphs to model asymmetric relationships such as one-way streets, precedence constraints, or flow networks. Within the context of graph theory, directed graphs extend the study of connectivity, paths, cycles, and components by incorporating direction, leading to specialized concepts like strongly connected components, directed acyclic graphs, DAGs, and reachability. These structures are crucial for algorithms in computer science, operations research, and network analysis, enabling the representation and solution of problems involving hierarchical structures, scheduling, and data flow. Weighted graphs. Weighted graphs are a fundamental concept within graph theory, a branch of mathematics that studies the properties and applications of graphs. In the context of graph theory, a weighted graph is a graph in which each edge is assigned a numerical value, called a weight. These weights typically represent quantities such as cost, distance, capacity, or any other metric relevant to the problem being modeled. Unlike unweighted graphs, where edges simply indicate connections, weighted graphs provide additional information that allows for more nuanced analysis and problem solving. For example, weighted graphs are essential in shortest path algorithms like Dijkstra's or the Bellman-Ford algorithm, where the goal is to find the minimum total weight path between vertices. They also play a crucial role in network optimization, resource allocation, and modeling real-world systems such as transportation networks, communication networks, and social networks. Understanding weighted graphs within graph theory involves studying their structure, properties, and algorithms that leverage edge weights to solve complex problems efficiently. Network flows. Network flows is a specialized area within graph theory that focuses on the study and analysis of flow networks, which are directed graphs where each edge has a capacity and each edge receives a flow. The primary goal in network flows is to determine the optimal way to send flow through the network from a designated source vertex to a sink vertex without violating capacity constraints on the edges. This involves solving problems such as the maximum flow problem, where the objective is to maximize the total flow from the source to the sink, and the minimum cut problem, which identifies the smallest set of edges that, if removed, would disconnect the source from the sink. Network flows leverage fundamental graph theory concepts such as paths, cuts, and connectivity, and employ algorithms like the Ford-Fulkerson method, Edmonds-Karp algorithm, and Dinnick's algorithm to efficiently compute flows. These concepts are crucial in various applications including transportation, communication networks, and supply chain logistics, making network flows a vital subfield within graph theory that bridges theoretical graph properties with practical optimization problems. Graph isomorphism. Graph isomorphism is a fundamental concept within graph theory that deals with the equivalence of graphs in terms of their structure. Two graphs are said to be isomorphic if there exists a one-to-one correspondence between their vertex sets that preserves adjacency. That is, vertices connected by an edge in one graph correspond to vertices connected by an edge in the other graph. This concept is crucial because it allows mathematicians to classify graphs based on their intrinsic connectivity properties rather than superficial labeling or representation. Determining whether two graphs are isomorphic involves finding such a bijection or proving none exists, which is a non-trivial problem with significant implications in areas like chemistry, computer science, and combinatorics. Within graph theory, understanding graph isomorphism helps in studying graph invariance, automorphisms, and the broader classification and characterization of graphs. Mathematical physics. Mathematical physics is a specialized branch of mathematics that focuses on the application of mathematical methods to problems in physics. Situated within the broader discipline of mathematics, it bridges abstract mathematical theories and physical phenomena, providing rigorous frameworks to formulate and solve physical problems. Unlike pure mathematics, which is concerned with abstract structures and proofs, mathematical physics emphasizes the development and use of mathematical tools, such as differential equations, functional analysis, and geometry, to model and understand the laws governing the physical universe. This field plays a crucial role in advancing both mathematics and physics by translating physical intuition into precise mathematical language, enabling the prediction and explanation of complex systems ranging from classical mechanics to quantum field theory. Classical mechanics. Classical mechanics, within the context of mathematical physics, serves as a foundational framework that mathematically describes the motion of physical bodies under the influence of forces. Unlike the broader discipline of mathematics, which encompasses abstract structures and theories, mathematical physics focuses on applying rigorous mathematical methods to solve physical problems. Classical mechanics specifically employs differential equations, variational principles, and geometric methods to model and analyze the trajectories, velocities, and accelerations of particles and rigid bodies. It bridges abstract mathematical concepts such as symplectic geometry and Hamiltonian and Lagrangian formalisms with tangible physical phenomena, enabling precise predictions of system behavior. This integration highlights how mathematical structures underpin physical laws, making classical mechanics a critical subfield that exemplifies the synergy between mathematics and physics in mathematical physics. Quantum mechanics. Quantum mechanics, within the context of mathematical physics, is a fundamental branch that uses rigorous mathematical frameworks to describe and predict the behavior of physical systems at microscopic scales. Unlike classical mechanics, which deals with macroscopic phenomena, quantum mechanics relies on complex mathematical structures such as Hilbert spaces, operators, and spectral theory to model the probabilistic nature of particles and their interactions. It formalizes concepts like wave functions, observables, and quantum states through linear algebra and functional analysis, providing precise tools to analyze phenomena such as superposition, entanglement, and quantization. By embedding physical principles into a solid mathematical foundation, quantum mechanics bridges abstract mathematical theories with empirical physical observations, enabling the development of technologies like quantum computing and quantum cryptography. This interplay between mathematics and physics exemplifies the core aim of mathematical physics: to formulate and solve physical problems using advanced mathematical methods. Statistical mechanics. Statistical mechanics, within the context of mathematical physics, is a rigorous framework that connects the microscopic properties of individual particles with the macroscopic observable phenomena in physical systems. It employs mathematical tools such as probability theory, measure theory, and functional analysis to model and analyze large ensembles of particles, typically in thermodynamic equilibrium. By using statistical methods, it derives thermodynamic quantities like temperature, pressure, and entropy from the underlying microscopic states governed by classical or quantum mechanics. This discipline bridges the gap between deterministic laws at the particle level and emergent statistical behaviors at the system level, providing a foundational understanding of phase transitions, fluctuations, and transport phenomena. In mathematical physics, statistical mechanics is essential for formulating precise mathematical models that describe complex physical systems, ensuring consistency with both physical principles and mathematical rigor. Quantum field theory. Quantum field theory, QFT, is a fundamental framework within mathematical physics that unifies classical field theory, special relativity, and quantum mechanics. It provides the mathematical structure and tools to describe and analyze the behavior of quantum fields, which are the underlying entities representing particles and their interactions. In the context of mathematical physics, QFT is studied rigorously to understand the properties of fields, such as locality, causality, and symmetry, using advanced mathematical concepts like operator algebras, functional analysis, and topology. This discipline bridges abstract mathematical theories with physical phenomena, enabling precise formulations of particle creation and annihilation, scattering processes, and gauge symmetries. By embedding QFT within mathematical physics, researchers aim to establish a consistent and rigorous foundation for quantum theories that describe fundamental forces and particles, facilitating deeper insights into both mathematics and theoretical physics. General relativity. General relativity is a fundamental theory within mathematical physics that describes gravitation as the curvature of spacetime caused by mass and energy. Unlike Newtonian gravity, which treats gravity as a force acting at a distance, general relativity formulates gravity through the geometry of a four-dimensional manifold equipped with a metric tensor. This metric tensor satisfies the Einstein field equations, a set of nonlinear, partial differential equations derived from variational principles in differential geometry and tensor calculus. The theory integrates concepts from differential geometry, such as Riemannian curvature, geodesics, and manifolds, making it a rich subject of study within mathematical physics. General relativity not only provides accurate predictions for phenomena such as the bending of light, gravitational time dilation, and black holes, but also serves as a foundation for modern cosmology. Its mathematical framework exemplifies the deep interplay between abstract mathematical structures and physical laws, highlighting the role of rigorous mathematical methods in formulating and understanding physical theories. Mathematical methods in physics. Mathematical methods in physics is a specialized area within mathematical physics that focuses on the development and application of advanced mathematical techniques to solve physical problems. Unlike the broader discipline of mathematical physics, which studies the mathematical foundations and structures underlying physical theories, this topic emphasizes practical tools and methods such as differential equations, linear algebra, complex analysis, group theory, and functional analysis. These methods enable physicists to model, analyze, and predict physical phenomena with precision. By integrating rigorous mathematical frameworks with physical intuition, mathematical methods in physics serves as a bridge between abstract mathematical concepts and their concrete applications in areas like quantum mechanics, statistical mechanics, and classical field theory. This topic is essential for advancing both theoretical understanding and computational approaches within the immediate parent field of mathematical physics. Dynamical systems. Dynamical systems, within the context of mathematical physics, refers to the study of systems that evolve over time according to a fixed rule, often described by differential equations or discrete mappings. This field bridges mathematics and physics by providing rigorous frameworks to model and analyze the temporal behavior of physical systems, ranging from classical mechanics to quantum systems. In mathematical physics, dynamical systems theory helps in understanding stability, chaos, and long-term behavior of physical phenomena by examining trajectories in phase space, invariant measures, and attractors. It also plays a crucial role in formulating and solving problems related to integrable systems, Hamiltonian dynamics, and statistical mechanics, thereby offering deep insights into the fundamental laws governing physical processes. Integrable systems. Integrable systems, within the context of mathematical physics, refer to a special class of dynamical systems that can be solved exactly and possess a rich mathematical structure. These systems are characterized by the existence of a maximal set of conserved quantities, which allows for the complete integration of their equations of motion. Unlike generic physical systems that often require numerical methods or perturbative approaches, integrable systems admit explicit analytical solutions, making them invaluable for understanding fundamental phenomena in physics. They appear in various areas such as classical mechanics, quantum mechanics, and statistical physics, often serving as idealized models that reveal deep insights into nonlinear dynamics, soliton theory, and symmetry properties. The study of integrable systems bridges mathematical techniques such as differential equations, algebraic geometry, and representation theory with physical concepts, thereby enriching both the theoretical framework and practical applications within mathematical physics. Mathematical foundations of physics. Mathematical foundations of physics, situated within the broader field of mathematical physics, focuses on the rigorous mathematical structures and principles that underpin physical theories. Unlike general mathematical physics, which often emphasizes the application of mathematical methods to solve physical problems, this topic delves into the axiomatic and conceptual basis of physical laws. It involves the study of foundational mathematical frameworks such as functional analysis, differential geometry, operator algebras, and category theory to provide precise formulations of physical concepts like space, time, matter, and energy. This foundational approach ensures consistency, clarity, and logical coherence in the development of physical theories, facilitating deeper insights into quantum mechanics, relativity, and field theories. By establishing a solid mathematical groundwork, it bridges abstract mathematical constructs with physical intuition, enabling the advancement of both mathematics and physics in a mutually enriching manner. Optimization. Optimization within the discipline of mathematics is the study of selecting the best element from a set of available alternatives based on a specific criterion. As a subfield of mathematics, it focuses on formulating and solving problems where the goal is to maximize or minimize a function by systematically choosing input values from an allowed set and computing the value of the function. Optimization encompasses various methods and theories, including linear programming, nonlinear optimization, convex analysis, and combinatorial optimization, among others. These methods rely heavily on mathematical concepts, such as calculus, algebra, and geometry, to analyze and solve problems efficiently. In the context of mathematics, optimization provides essential tools for modeling and solving real-world problems in economics, engineering, operations research, and data science, where determining the most effective or efficient solution is critical. By leveraging mathematical rigor, optimization ensures solutions are not only feasible, but also optimal with respect to the defined objective and constraints. Linear optimization. Linear optimization, also known as linear programming, is a subfield within optimization that focuses on maximizing or minimizing a linear objective function subject to a set of linear equality and inequality constraints. Unlike general optimization, which may involve nonlinear or non-convex problems, linear optimization deals specifically with problems where both the objective function and the constraints are linear expressions. This structure allows for efficient solution methods such as the simplex algorithm and interior point methods. Linear optimization is fundamental in various applications, including resource allocation, production planning, transportation, and network flows, where decisions must be optimized under linear constraints. Within the broader context of optimization, linear optimization serves as a foundational topic that illustrates key concepts such as feasibility, boundedness, duality, and sensitivity analysis, which are essential for understanding more complex optimization problems. Nonlinear optimization. Nonlinear optimization is a specialized branch within the broader field of optimization that focuses on problems where the objective function or some of the constraints are nonlinear. Unlike linear optimization, where relationships are expressed as linear equations or inequalities, nonlinear optimization deals with more complex mathematical models that can capture a wider range of real-world phenomena. In the context of optimization, nonlinear optimization extends the fundamental goal of finding the best solution, such as maximizing or minimizing an objective function, by addressing challenges posed by nonlinearity, including multiple local optima, non-convexity, and differentiability issues. Techniques in nonlinear optimization include gradient-based methods, such as steepest descent and Newton's method, as well as derivative-free methods like genetic algorithms and simulated annealing. These methods are crucial for solving practical problems in engineering, economics, machine learning, and other fields where the assumption of linearity is too restrictive. Thus, nonlinear optimization enriches the optimization discipline by providing tools and theories to handle more realistic and complex optimization problems. Integer optimization. Integer optimization is a specialized branch of optimization that focuses on problems where some or all of the decision variables are restricted to integer values. Unlike continuous optimization, where variables can take any real values within given bounds, integer optimization deals with discrete variables, making the problem combinatorial in nature. This constraint significantly increases the complexity of the problem, as the solution space becomes non-convex and often requires different algorithmic approaches such as branch and bound, cutting planes, and heuristic methods. Integer optimization is essential in many practical applications where solutions must be whole numbers, such as scheduling, resource allocation, and network design. Within the broader field of optimization, integer optimization extends classical techniques to handle the discrete nature of variables, bridging the gap between continuous optimization methods and combinatorial problem-solving. Convex optimization. Convex optimization is a specialized branch within the broader field of optimization that focuses on problems where the objective function is convex, and the feasible region is defined by convex constraints. Unlike general optimization problems, convex optimization problems have the crucial property that any local minimum is also a global minimum, which significantly simplifies both theoretical analysis and algorithmic solutions. This characteristic arises because convex functions curve upwards, ensuring no multiple local minima exist. Within the context of optimization, convex optimization provides powerful tools and methods to efficiently solve a wide range of practical problems in engineering, economics, machine learning, and statistics. Techniques such as gradient descent, interior point methods, and subgradient methods are tailored to exploit convexity, leading to robust and scalable algorithms. Moreover, the study of duality in convex optimization offers deep insights into problem structure and solution properties, enabling more effective problem formulations and sensitivity analyses. Thus, convex optimization serves as a foundational pillar in optimization, bridging theoretical rigor with practical applicability. Combinatorial optimization. Combinatorial optimization is a specialized area within the broader field of optimization that focuses on problems where the set of feasible solutions is discrete or can be reduced to a discrete one. Unlike continuous optimization, where variables can take any value within a range, combinatorial optimization deals with finding an optimal object from a finite set of objects. This often involves structures such as graphs, permutations, subsets, or sequences. The goal is to optimize an objective function, such as minimizing cost, maximizing efficiency, or finding the shortest path, subject to certain constraints. Typical problems include the traveling salesman problem, knapsack problem, and graph coloring. Techniques used in combinatorial optimization include exact algorithms like branch and bound, cutting planes, and dynamic programming, as well as approximation algorithms and heuristics when exact solutions are computationally infeasible. By focusing on discrete structures, combinatorial optimization extends the principles of optimization to complex, real-world problems where decisions are inherently combinatorial in nature. Stochastic optimization. Stochastic optimization is a subfield of optimization that focuses on solving optimization problems under uncertainty. Unlike deterministic optimization, where all parameters and data are known and fixed, stochastic optimization deals with scenarios where some elements are random or probabilistic. This approach is essential when the objective function, constraints, or both depend on random variables or noisy data, making traditional optimization methods insufficient. Within the broader context of optimization, stochastic optimization methods incorporate randomness, either in the problem formulation or the algorithmic process, to find solutions that are robust or optimal in expectation. Common techniques include stochastic gradient descent, sample average approximation, and stochastic programming. These methods are widely applied in fields such as finance, engineering, machine learning, and operations research, where decision-making under uncertainty is critical. Multi-objective optimization. Multi-objective optimization is a specialized branch within the broader field of optimization that focuses on problems involving more than one objective function to be optimized simultaneously. Unlike single-objective optimization, where the goal is to find a single best solution, multi-objective optimization seeks to identify a set of optimal trade-offs known as Pareto optimal solutions. These solutions represent scenarios where no objective can be improved without degrading at least one other objective. This complexity arises because objectives often conflict, requiring methods that balance competing criteria effectively. Techniques in multi-objective optimization include evolutionary algorithms, scalarization methods, and Pareto front approximations, which help decision-makers understand the trade-offs and select solutions aligned with their preferences. Within the context of optimization, multi-objective optimization extends traditional concepts by addressing the challenges of multiple criteria, thereby enabling more comprehensive and realistic modeling of real-world problems where multiple goals must be considered simultaneously. Dynamic optimization. Dynamic optimization is a specialized branch within the broader field of optimization that focuses on problems where decisions are made sequentially, over time. Unlike static optimization, which deals with a single decision at a fixed point, dynamic optimization addresses scenarios where the outcome depends on a series of interrelated decisions and evolving states. This approach is essential for modeling and solving problems in which the system's state changes dynamically, and future decisions depend on current and past states. Techniques in dynamic optimization often involve formulating the problem using state variables, control variables, and dynamic constraints, and solving it through methods such as dynamic programming and the calculus of variations. Applications span economics, engineering, finance, and operations research, where optimal policies or control strategies must be determined over time to maximize or minimize an objective function subject to dynamic system behavior. Global optimization. Global optimization is a subfield of optimization focused on finding the absolute best solution to a problem within a given set of constraints, rather than just a locally optimal one. While optimization broadly involves selecting the best element from some set according to a criterion, global optimization specifically addresses challenges where the objective function may have multiple local optima, making it difficult to identify the true global optimum. Techniques in global optimization often involve strategies to avoid getting trapped in local optima, such as stochastic methods, branch and bound algorithms, and deterministic global search methods. This discipline is crucial in applications where the quality of the solution significantly impacts performance, and local optima are insufficient or misleading. Thus, global optimization extends the principles of optimization by emphasizing comprehensive search strategies and rigorous guarantees to locate the best possible solution across the entire feasible domain. Derivative-free optimization. Derivative-free optimization is a subfield within optimization that focuses on solving optimization problems without relying on derivative information of the objective function. Unlike traditional optimization methods that use gradients or Hessians to guide the search for optima, derivative-free methods are designed for scenarios where derivatives are unavailable, unreliable, or expensive to compute. This situation commonly arises in black box optimization problems, simulation-based optimization, or when the objective function is noisy, discontinuous, or non-differentiable. Within the broader context of optimization, derivative-free optimization methods employ strategies such as direct search, pattern search, evolutionary algorithms, surrogate models, and trust region approaches to iteratively explore the search space and approximate optimal solutions. These methods balance exploration and exploitation by using function evaluations alone, making them particularly valuable for complex real-world problems where gradient information cannot be easily obtained or does not exist. Game theory. Game theory is a branch of mathematics that studies strategic interactions among rational decision-makers within the broader field of mathematics, which provides the foundational tools and frameworks for precise reasoning and problem-solving. Game theory applies mathematical models to analyze situations where the outcome for each participant depends on the choices of all involved. It formalizes concepts such as strategies, payoffs, and equilibrium, enabling the prediction and explanation of behavior in competitive and cooperative scenarios. By leveraging mathematical structures like matrices, graphs, and probability theory, game theory extends mathematical analysis to social, economic, and biological contexts where multiple agents interact, making it a vital subdiscipline that bridges abstract mathematical theory with practical decision-making processes. Cooperative game theory. Cooperative game theory is a branch of game theory that focuses on predicting which coalitions of players will form, the joint actions these coalitions will take, and how the collective payoff will be distributed among the members. Unlike non-cooperative game theory, which analyzes strategic interactions where players act independently and binding agreements are not enforceable, cooperative game theory assumes that players can negotiate and form binding agreements to achieve mutually beneficial outcomes. This area studies concepts such as the core, the Shapley value, and the bargaining set, which provide methods for allocating payoffs fairly and stably within coalitions. Cooperative game theory is particularly useful in scenarios where collaboration and coalition formation are essential, such as in economic partnerships, political alliances, and networked systems. It extends the foundational principles of game theory by emphasizing cooperation, collective strategy, and equitable distribution of gains among cooperating agents. Non-cooperative game theory. Non-cooperative game theory is a branch of game theory that focuses on predicting the outcomes of games where players make decisions independently and without collaboration. Unlike cooperative game theory, which studies how groups of players can form binding agreements and coalitions, non-cooperative game theory analyzes strategic interactions where each player aims to maximize their own payoff, often in competition with others. It models scenarios where communication and enforceable contracts are absent, emphasizing individual rationality and strategic behavior. Key concepts include Nash equilibrium, where no player can benefit by unilaterally changing their strategy, and extensive form games, which represent sequential moves. This topic is fundamental within game theory, as it provides the tools to analyze and predict the behavior of self-interested agents in economics, political science, and beyond, under conditions of strategic interdependence without cooperation. Evolutionary game theory. Evolutionary game theory is a subfield of game theory that applies the principles of evolution and natural selection to strategic interactions among populations of agents. Unlike classical game theory, which often assumes fully rational players making calculated decisions, evolutionary game theory focuses on how strategies evolve over time based on their success or fitness within a population. It models the dynamics of strategy frequencies using replicator equations and other evolutionary dynamics, emphasizing how certain strategies become stable or dominant through repeated interactions and adaptation. This approach is particularly useful for understanding behaviors in biology, economics, and social sciences, where agents may not be perfectly rational, but adapt based on the success of strategies in their environment. By integrating evolutionary concepts, evolutionary game theory extends the traditional framework of game theory to analyze how strategic behavior emerges and stabilizes in populations over time. Repeated games. Repeated games are a fundamental concept within game theory, focusing on scenarios where the same strategic interaction, or stage game, is played multiple times by the same players. Unlike one-shot games, repeated games allow players to observe past actions and outcomes, enabling strategies that depend on the history of play. This temporal structure introduces the possibility of cooperation, punishment, and reputation effects that are not present in single-shot games. In the context of game theory, repeated games help explain how cooperation can emerge among rational players, even when individual incentives might favor defection in a one-time interaction. The analysis of repeated games involves studying equilibrium concepts, such as subgame perfect equilibrium and Folk theorems, which characterize the range of possible outcomes sustained by credible threats and promises over time. Overall, repeated games enrich the study of strategic behavior by incorporating the dynamic aspect of interaction and the impact of future consequences on present decisions. Stochastic games. Stochastic games are a class of dynamic games that extend the framework of game theory by incorporating probabilistic state transitions. Unlike static games where players make decisions simultaneously or sequentially without changing the environment, stochastic games model situations where the game evolves over time based on both the player's actions and inherent randomness. At each stage, the game is in a particular state, and players choose actions that determine not only their immediate payoffs, but also the probability distribution over the next state. This introduces a Markovian structure to the game, where future states depend only on the current state and players' actions. Stochastic games generalize repeated games and Markov decision processes, allowing for the analysis of strategic interactions in dynamic and uncertain environments. They are fundamental in studying long-term strategic behavior, equilibrium concepts like Markov perfect equilibrium, and have applications in economics, operations research, and evolutionary biology within the broader context of game theory. Bayesian games. Bayesian games are a fundamental concept within game theory that extend the analysis of strategic interactions to situations where players have incomplete information about each other. Unlike classical games where all players have complete knowledge of the game's structure and other players' payoffs, Bayesian games incorporate uncertainty by allowing players to have private information known as types, which affect their preferences and strategies. Each player holds beliefs about the types of other players, typically represented by a probability distribution, and these beliefs are updated according to Bayes' rule as the game progresses. The solution concept commonly used in Bayesian games is the Bayesian-Nash equilibrium, where each player's strategy maximizes their expected utility given their beliefs about other players' types and strategies. This framework is crucial for modeling real-world strategic situations such as auctions, negotiations, and signaling, where asymmetric information plays a key role. By integrating incomplete information into the strategic analysis, Bayesian games provide a richer and more realistic understanding of strategic behavior compared to traditional complete information games. Algorithmic game theory. Algorithmic game theory is a subfield of game theory that focuses on the design and analysis of algorithms for solving game-theoretic problems, particularly those arising in computer science and economics. While game theory studies strategic interactions among rational agents and the outcomes of these interactions, algorithmic game theory emphasizes computational aspects, such as how to efficiently compute equilibria, design mechanisms that incentivize truthful behavior, and analyze the complexity of strategic decision-making processes. This discipline bridges the gap between theoretical models of strategic behavior and practical algorithmic solutions, addressing challenges like scalability, approximation, and robustness in multi-agent systems. It plays a crucial role in understanding and designing systems where autonomous agents interact, such as online auctions, network routing, and resource allocation, all within the broader framework of game theory. Coalition formation. Coalition formation is a fundamental concept within game theory that studies how groups of players, called coalitions, form and cooperate to achieve collective outcomes that may be unattainable individually. In the context of game theory, which analyzes strategic interactions among rational decision-makers, coalition formation focuses on the rules and mechanisms by which players decide to join forces, share resources, or coordinate strategies to improve their payoffs. This area examines the stability and fairness of coalitions, the distribution of gains among members, and the conditions under which coalitions emerge or dissolve. Key models include cooperative games with transferable utility, where the value generated by a coalition can be freely distributed among its members, and solution concepts such as the core, the Shapley value, and the bargaining set that help predict or prescribe how coalitions form and how benefits are allocated. Understanding coalition formation is crucial for analyzing scenarios in economics, political science, and computer science, where collective action and collaboration influence strategic outcomes. Mechanism design. Mechanism design is a subfield of game theory that focuses on designing rules or systems, mechanisms, to achieve desired outcomes, even when participants have private information and act strategically. Unlike traditional game theory, which analyzes given games and predicts outcomes, mechanism design works in reverse. It starts with a desired objective and seeks to construct a game or mechanism that leads rational agents to achieve that objective through their strategic interactions. This involves creating incentives so that individuals reveal their true preferences or types, enabling efficient allocation of resources, optimal decision-making, or fair outcomes. Mechanism design has applications in auctions, voting systems, public goods provision, and contract theory, where the designer cannot control participants directly but can influence outcomes by structuring the rules of the game. Auction theory. Auction theory is a specialized branch within game theory that studies how individuals or entities strategically bid in auctions to acquire goods or services. It analyzes the rules and formats of auctions, the strategies employed by bidders, and the outcomes in terms of efficiency, revenue, and fairness. Since game theory focuses on strategic interactions among rational decision-makers, auction theory applies these principles to scenarios where multiple participants compete by submitting bids, each aiming to maximize their own payoff. It models various auction types, such as English, Dutch, sealed bid, and Vickrey auctions, and examines equilibrium bidding strategies, information asymmetry, and incentive compatibility. By understanding these strategic behaviors and outcomes, auction theory provides insights into designing auctions that achieve desired objectives within competitive environments characterized by strategic interdependence, which is central to game theory. Conclusion. This has been Gorm the Old's The Big Ideas in Mathematics reading, read by me, the Guard from Oblivion. Thanks for listening, and please like and subscribe.